Welcome to this session on testing, concurrency, testing, and verification. Our first talk will be given by Alexander Moine, and it will be on will it fit, verifying heap space bounds of concurrent programs under garbage collection. Over to you.
Thank you. All right. So, welcome everyone. My name is Alexandre Moine. I'm currently a postdoc at NYU, and before that, I was a PhD student with Arthur Chargueroux and François Potier at INRIA Paris. So this corresponds to the last part of my PhD thesis, and this is a top-class paper. And the title of this paper is Will it fit, verifying heap space bounds of concurrent programs under garbage collection. So the motivation, the idea, we need to verify heap space bounds because a program that will use too much memory will crash. So in some sense, heap space bounds are as important as functional correctness. Here we are going to use separation logic. It's a separation logic talk. And the overall idea is to use one diamond here to represent one space credit or one free memory word. This is an old idea dating back to Hoffman in 1999. And so space credits are resources of separation logic. So if we have here, for example, N1 plus N2 space credits, you have N1 and N2 space credits. This is the separating conjunction. And in the case of manual memory management in languages such as C, things are conceptually easy, because allocation consumes space, so allocating a block of size 1 consumes 1 space credit and produces a points to assertion. And dually, deallocation, freeing allocation L, consumes a points to assertion and produces a space credit. And then the soundness theorem of such a logic is that if you are able to verify the program T under the precondition of capital S space credits, then T is safe and will not run out of memory with a heap of a size at least capital S. So end of my PhD thesis? No, of course, because of garbage collection. So languages such as Java or POPL' have a garbage collector, a GC, that runs together with the program. And then from time to time, the GC will deallocate unreachable blocks for which we are sure the program will not use them anymore. So this is great because garbage collection greatly simplifies the life of the programmer. There is no need to write free, so no free-related bugs. However, from the point of view of the prover, it makes things difficult because we do not have any syntactical point in the program where to recover space credits. So this generated a line of work. It was started by Madu and Potier in 22, where they targeted a very low-level language, assembly-like, with the GC and with concurrency primitives, but they do not provide any example. In the first year of my PhD thesis, I scaled up to a high-level language, similar to OCaml, but dropping out concurrency for simplicity. And as you can guess, in this work, we bring everything back together. It's for a high-level language with a concurrent primitive. So the contribution of this work is IRIS-FIT, the first separation logic for verifying heap space bounds in a high-level concurrent language equipped with a GC. Think of OCaml. This includes a formal account of unreachability and roots, a category of locations I'm going to define later. We also propose new realistic language constructs that we call protected sections and polling points to improve heap space bounds of lock-free data structures. And we also have several case studies and a soundness proof, and everything is mechanized in the ROC prover on top of the IRIS framework. So I will first focus on unreachability and roots, and then talk about this new language construct. So as I said, the challenge here is where to recover space when we are proving the program. And the key idea comes from Madu and Potier in 22, where they change the meaning of a space credit, and they say that one space credit asserts that one memory word is free or can be freed by the next GC. And this is very cool because it enables what we call a logical deallocation rule, meaning that in the proof, during the proof, if I know that L is a valid location and L is unreachable, then this is a ghost update. So just by shifting my view of the state, I can generate one space credit because I know that the location can be deallocated. So now the question is how to prove that a location is unreachable. So we have to understand how the GC computes reachability. And the set of reachable locations is computed from the root, again, this famous set I'm going to define, following heap path. So this means that to prove that a location is unreachable, you have to prove that the location is not a root and is itself not reachable by any transitively reachable heap cell. So in order to prove these two facts, we have two new separation logic assertions, the pointed by thread assertion and the pointed by heap assertion. Let me start by the latter. So the pointed by heap assertion, it's a contribution by Kessos and Kritikos and was refined by Madiot and Potier. And it's a dual of the points to assertion. So we say the location L is pointed by the multiset of locations capital A. It's a multiset because multiplicity matters. And the interpretation of this assertion is that when L is pointed by capital A, we know that A is an over-approximation of the reachable predecessors of L. In particular, when L is pointed by the empty multiset, you know that L has no reachable predecessors and might be eligible for deallocation. So pointed by heap assertions evolve on a store operation. This is a very simplified store operation. But for example, if we are going to write W inside L, and if we know that L points to V, that V is pointed by L, and that W has no predecessors, then after the store operation, we know that L points to W, that V now has no predecessor. We remove the link from link to L to V, but now W has one predecessor, L. And technically, we improve these assertions with fraction zero and negative multisets. If you're curious, read the paper. All right, now about these roots. So the question is, what are the roots considered by real-life GCs? Here we follow the free variable rule that was introduced by Felison and Hibb in '92. And they say that in a substitution-based semantics, the roots are the locations occurring in the threads that remain to be evaluated. Let me show you an example. If you have a single thread here, let A equals ref 4, in let B equals ref 2, in bank A plus bank B, and we start with no roots. Then first thing, we allocate the ref of 4, so we have a new location, LA, and LA is definitely a root. It should not be deallocated. Then we substitute A by its value, LA. LA still occurs in the program, so LA is still a root of the program. Then we allocate the ref of 2. We get a new location, LB. We substitute B with its value. Then we dereference LA. And then you can see here that LA does not occur anymore in the program that remains to be evaluated, so LA is not a root, and here can be deallocated. LB, however, is still a root. So, but then when we dereference it, we have no roots anymore. Okay, so how to track roots at the logical level? First of all, we need a way of naming threads in the logic. So we add a ghost thread identifier, pi, here, to say that the term T is being executed by pi. And then we have a pointed by thread assertion that is similar to the pointed by heap assertion. It's a fractional assertion, but I will not show the details here. So it reads that L is pointed by capital pi. Capital pi is a set of thread identifiers. And L is pointed by capital pi, asserts that capital pi is again an over-approximation, but in this case of the threads in which L is a root. So in particular, if L is pointed by the empty set, then L is not a root and may be eligible for deallocation. A load operation, for example, updates a pointed by thread assertion. So again, it's a simplified version, but if we load the location L and we know that L points to L prime and L prime is not a root of any thread, then if we do this operation of thread pi, we obtain L prime. L still points to L prime, and now L prime is a root of thread pi. Now, how to prove that the location is not a root anymore, how to trim this pointed by thread assertion. You have to read this rule from bottom to top. So if we are currently verifying thread pi, executing T, and if we know that L may be a root of thread pi, well, if we are able to syntactically prove that L does not occur in the set of locations inside T, then we can trim the pointed by thread assertion and deduce that L is not a root of any thread. And with all of that at hand, the trimming rule requires a non-standard bind rule, but it's a contribution from previous work, so it is a paper. And with all of that at hand, recall that our goal was to prove that L is unreachable. Now we have a way of proving that L is unreachable. We just need to provide the empty pointed by heap and the empty pointed by thread assertions to deduce that L is unreachable and that we can produce a space credit. So you are all waiting for it, the Sandler theorem of the logic. If we are able to verify the program T under the precondition of capital S space credits, then we know that the execution of the program T with a heap of size at least S cannot reach a stack configuration, and if one thread needs space, then stopping all threads and running the GC will free up enough memory. So this is what we call a stop the world semantics, and it's a good approximation of what actual GCs are doing. And with this logic, we can actually verify the space complexity of a concurrent counter, locks, and even more things. But we have an issue. And we have an issue with lock-free data structures. So here is one lock-free data structure. It's the Traber's stack. It's a linearizable lock-free stack implemented as a reference on an immutable list. So you have your reference here and an immutable list. And if we try to push a value on the stack, so to push here, for example, V0, we construct a new list cell and try to update this pointer to this pointer using an atomic compare and swap operation. If it fails to do some other threads, then we loop. Then the pop operation is very symmetrical. I have the code here. So if we try to pop a value of the stack S, we first load the content of S. We ignore the case where the stack is empty. And if the stack is non-empty, if we have a head Y and a tail YS, we try to update the stack from XS to YS using an atomic compare and swap. What should be the specification of this stack? Brace yourself. This is an atomic triple. So it's a fancy triple. Here you can think of the line as separating conjunction, but this triple guarantees that the bottom precondition will be updated atomically into the bottom post condition. So the stack is linearizable. So here, if we try to push the value V inside LS, well, we will need space to allocate the list cell, and we require the stack to be of model capital L. And in the post condition, we know that we push the values, so the stack is of model V const with L. Now, if we try to pop a value of the stack, we require the stack to be non-empty and of model V const with L. And in the post condition, we know that the stack is of model L, that we return the value V, and we would like to have some space here to recover the space of the popped cell. However, this specification is false, and it's not an issue of iris fit. It's an issue that some interleavings are actually invalidating this specification. Let me show you one of these interleavings. So here we have two concurrent threads that are going to pop values of the stack, and the left thread is going to execute, so we enter the body of pop. It loads the content of LS, which is LXS. And then this thread is going asleep, and the right thread is going to successfully pop values of the stack. And then this thread faces a big allocation. Here we have an issue because the sleeping thread here maintains reachable LXS, but also all the successors of LXS. So it means that we have no free space. The GC will not be able to deallocate these locations. So the allocation will fail. So the question here is that can we devise new language constructs to prevent these interleavings? The answer is yes, and let me show you them. The first thing we propose is protected sections. So here the observation is that the location LXS is a root, indeed, but it's a root for a very short amount of time. It's a root until the CAS executes, that is, until the CAS succeeds or fails. So the idea is that the location should wait until LXS is released before running the GC. So here we introduce the protected sections that delimitate where we have where LXS is a temporary root. So it has a single entry point but multiple exit points. Then in details, each thread is either outside or inside the protected section, and the GC runs only when every thread is outside protected sections. This prevents the for problematic interleaving because an allocation that will exceed the available memory waits for the GC to run, but the GC itself waits for protected sections to end, releasing their temporary roots. Some constraints inside protected sections, we allow no allocation because an allocation might trigger the GC, but we prevent GC inside protected sections, no divergence, and no nesting. Then we adapt reasoning rules in ArraysFit to reason about these protected sections. So the idea is that a location that is reachable only from protected sections will be unreachable by the time the GC runs, because we know that the GC waits for every thread to exit their protected sections before running. So at the logical level, we have some rules that enable an escape hatch to the pointed by thread discipline. And in particular, they allow early trimming, that is to pretend that the location is not a root anymore because it's a root only in protected sections. And we allow also early logical deallocation, that is, we allow deallocation of things that are reachable only from protected sections. And then with these rules, trust me, everything is verified. We are able to actually verify this ripple for POP. But then we just created another issue because it means that we may have a liveness problem. Indeed, if you have an adversarial scheduler, due to protected sections, you might delay the GC forever because you have this big allocation that needs a GC. But here, if you have a thread that just enters and exits protected section, well, a scheduler might choose to schedule this thing and never run the GC. So in order to prevent this kind of interleavings, we introduce polling points. And the semantics is simple. A thread facing a polling point stops its execution until no other thread requires a GC. And in the paper, we proved that we can guarantee liveness if we introduce a polling point in every loop. Back to reality, these protected sections and polling points are realistic because they are inspired by what we call safe points, which are a technique to implement the stop-the-world garbage collector of OCaml. Safe points, conceptually, both delimit protected sections and act as polling points. But here, what we propose is to ask the programmer to be explicit about protected sections, about these dangerous states, but to let the compiler insert polling points. As future work, we have several venues, for example, integration with verified compiler, in the sequential case with KKML, for example. Also, we would like to compare with safe memory reclamation schemes, which are kind of handmade GCs for languages such as C. But also, we would like to investigate how our system can be used as a foundation for type systems, like the AARA line of work by Hoffman. Also some practical applications, adding protected sections for OCaml and providing some control over polling point positions. And some theoretical extensions with more advanced case studies, like the Harris list, and also weak pointers and ephemerons that are data structures that are not followed by the GC, and they are especially difficult to specify and verify. In conclusion, so I just presented ArraysFit, the first separation logic for verifying heap space bound in a high-level concurrent language equipped with a GC. The key ingredients were space credits to keep track of the available heap space, the pointed by heap and pointed by thread assertions to prove unreachability, protected sections to improve heap space bounds of log-free data structures, and polling points to recover liveness. We have several case studies, so logs, traverse stacks, and even the Maker and Scott's queue. And everything is mechanized, and there is more in the paper, in particular rules for cycles and closures. And with that, thank you for your attention.
There's lots of time for questions.
Right. Thank you for the talk. Hello. I was wondering about your take on have the programmer insert the critical section, and I was wondering why you'd prefer that to you mentioned save points,
Yes.
which are inserted by the compiler. It just seems, how would I know where to insert the critical points? How can I look at this and think, this is a place where this route is short-lived. This is surely a critical section that I should insert manually.
So most of the time, you should not insert protected sections. But what we identified that there are really a problem in log-free data structures, and you should just write as big as possible protected sections inside log-free data structures.
Right, because this only becomes a problem. You only need protected sections when you have these log-free data structures.
We had these issues only with log-free data structures.
Right. So when if you're a programmer doing log-free data structures, you need to take this into consideration.
Yeah, you should care about them. Yeah.
And if you forget to, you'll have a big problem.
You might have a specific. Yeah.
So I was wondering, in the presence of the critical sections, can you explain why the soundness theorem still holds, or is it a bit modified then?
So the soundness theorem is the same, but we change the semantics. So now the GC is allowed to run only when every thread is outside a protected section. And by changing these semantics, we can say that when we verify the program, every allocation will succeed, because the allocation will wait for the GC to run, so we'd wait for every thread to exit their protected sections.
So sort of building on the previous question about protected sections and log-free data structures, I understand a protected section is not like is not a critical section protected by a lock in the pure sense, but surely it requires some synchronization?
Yes.
So then the data structure is no longer lock-free?
Yes, you're right. So first of all, the synchronization is introduced by polling points. These are the ones synchronizing. But this is already the case. Like the GC already synchronizes on these save points.
Okay, so I think we'll have to move on. So let's thank the speaker once again.
Thank you.
Okay, so our next talk will be presented by VR Satyanarayana. It's on verifying almost sure termination for randomized distributed algorithms.
Thank you. Hey everyone, I'm Satya. I'm here to talk about our work on verifying almost sure termination for randomized distributed algorithms. This is joint work with Konstantin, Rupak, and Harshit. So, our work studies the termination of randomized distributed algorithms. What are these things? Well, in general, distributed algorithms specify instructions to be followed by a number of independently executing processes. These instructions can have the processes change state locally, perhaps in a randomized way. It can also have the processes communicate via an unknown network. This network can ascribe arbitrary delays to the messages, and it is the job of the algorithm to be able to deal with such arbitrary delays. Now, in addition to having to deal with delays, the algorithms must deal with something called process faults. There are two kinds of process faults. The first are the crash faults, where a process just stops executing at some point, meaning it can no longer receive messages or send messages or do anything else. The second kind is a bit more fun. These are the Byzantine faults, where, like the Byzantine generals problem, we have traitorous processes that can send arbitrary messages with just the goal of disrupting algorithm execution. Right? So these are distributed algorithms. There are a number of reasons for having them. We have algorithms for leadership election. We have algorithms for maintaining shared ledgers. But in our work, we study the consensus algorithms for something a bit more fundamental called consensus. So in the case of consensus, we have a number of processes that each start with a binary value. And at the end of the algorithm, they all form consensus on the binary value. So consensus is a fundamental property of distributed systems. It is essential to showcase the reliability of the system in the presence of process faults. It's important to note that randomization is essential to achieve consensus. Right? These lovely folks over here have shown that there is no deterministic distributed algorithm that achieves consensus. And in the current world right now, there are a lot of algorithms for consensus. But unfortunately, the proofs that some of these algorithms come with are a bit intuitive and make some implicit assumptions. For example, Benor's algorithm was proved against a much weaker class of network behaviors and was proven correct for stronger behaviors much later. And there have even been published algorithms with liveness flaws, meaning that you could sequence message deliveries in these algorithms to ensure that they never terminate. Right? So because of all of these things, we wanted to look for machine-checked proofs that these consensus algorithms indeed terminate. And our way of tackling this problem is to use proof rules for termination. Proof rules in general are just ways to encode certificates of termination in a machine-checkable way. The most classic example of a proof rule for termination is the ranking functions. These guys just encode the length of the terminating run of a program, and this length must reduce at each step, right? And in our setting of non-deterministic probabilistic programs, there are already a number of existing proof rules for termination. And there are even some verification infrastructures where we could just implement one of the consensus algorithms and give it the proof rules, and we can get an yay. This algorithm does actually terminate, right? So how do we use these things exactly? Well, we use the non-determinism that these programming languages provide to serialize the execution of a distributed algorithm. At each point, we will take the global view of the distributed algorithm, non-deterministically pick one of the actions that are available there, and then use any of our AST hammers inside the AST toolbox to prove the termination of the system. Right? So this is a nice overarching plan, but unfortunately there is one problem. Distributed algorithms make implicit fairness assumptions. These assumptions are also transferred when we look at it as a probabilistic program. And these are quite simple assumptions, like every process must eventually execute infinitely often, and every message that is sent to the network will eventually be delivered by the network. Unfortunately, none of the existing proof rules for probabilistic termination incorporate fairness assumptions. And this exactly is where we come in. We have shown certificates for the almost sure termination of a number of consensus algorithms, including a broad general class of algorithms that use a binding crusader abstraction. using a new proof rule for almost sure termination that considers fairness. Okay? So in the rest of the talk, I will show you how we use this thing to prove the termination of the first algorithm that solves distributed consensus. Okay? This is Ben-Orr's algorithm. It is the first, and it's a quite simple and elegant solution to the problem of distributed consensus. And in this slide, I will show you what this algorithm's execution will look like for the case where you have 5 correct processes, and 1 Byzantine process. Okay? I will show you a synchronous execution because it is just simpler to show in a slide. So, Ben-Orr's algorithm proceeds through several rounds. Each round has 2 stages. Whenever a process enters a round, it enters with a Boolean value that it would like to propose. These are the ticks and the crosses next to the processes, right? And in the first stage, the process just broadcasts the value that it wants to propose to every other process in the network. Okay? And after broadcasting, it waits for 5 responses from the network. This 5 corresponds to the number of non-faulty processes in the network. And once it has all of these 5 messages, it analyzes them. It sets a local value to it checks if it has received 4 messages of the same type. If so, it sets a local variable to the value of those 4 messages. Otherwise, it sets them to question mark. This number 4 just corresponds to a way of determining majority in the presence of Byzantine faults. Okay? Now, after setting this internal variable, it just transmits this internal variable again to every other process. Note the action of the Byzantine process here. It can send whatever message it wants. And it indeed did send whatever message it wanted in the previous round, in the previous stage. Right? So, in the second stage, we broadcast this internal variable, and then you again wait for 5 messages. And after waiting, you get to analyze these messages and decide if you get to terminate or decide what you want to do in the next round. Okay? So, a process gets to terminate if it has received at least 4 messages of the same type. None of the processes here have managed this. So, what the processes can do is, if it has received at least 2 messages of the same type, it can propose the value of that message in the next round. This is what is happening to the processes on the left. And this value, too, is again just 1 more than the number of Byzantine processes that are in the network at the moment. Okay? And if processes don't even get this, the only thing they can do is toss a coin and propose the output of this tossed coin in the next round. Now, while I have presented a synchronized view of Ben-Orr's algorithm, it is important to remember that Ben-Orr's algorithm isn't really synchronous. It's for asynchronous consensus. Processes can be in different rounds at every possible state. Okay? Now, why is this algorithm correct? Well, it's correct for 2 pretty simple reasons. The first is that if all non-faulty processes begin a round of Ben-Orr with the same value, as is happening here, then the algorithm terminates in 1 round. This is not too difficult to show. And the more interesting thing is, let's say, the purpose of the coins, purpose of all the coin tossing. You can show that there exists a lucky sequence of coin tosses spanning 2 rounds, after which all non-faulty processes begin the next round with the same value. Meaning that if things go perfectly well, the algorithm will terminate in 3 rounds. This fact is exactly what we encode as certificates in our proof rules to verify the termination of this algorithm. Okay? Well, this is as good a point as any to segue into proof rules. Well, we talked about ranking functions earlier, but we want to actually analyze proving termination of probabilistic programs like this one. Ranking functions are not enough because here you decrement x or do nothing with equal probability, right? But you have to reduce with probability 1 every time in a ranking function. So to prove termination, generally speaking, we have shown last year that you need two kinds of certificates. The first certificates are called the probabilistic variants. They were introduced by McIver and Morgan in 2005. The second is a super martingale. This was studied a couple of times in the literature before. So the variants are a generalization of the idea of encoding the length of the terminating run. These ask for functions that reduce with a minimum probability at each execution step. So for this particular program over here, the simple function u of x is x is a variant. However, for variants to work, these functions have to be bounded, which can work for this program as long as you have a fixed initial state, right? However, for other programs, variants don't work. They're not enough. For example, in this program, a simple one-dimensional random walker, there exists no bounded variant that can work. And for this reason, we need super martingales. Super martingales essentially support the variants. They are simple functions that do not increase at each execution step. For the simple one-dimensional random walker over here, a simple super martingale that simply assigns, let's say, outputs the value of x at each state is a super martingale because it does not increase in expectation at each step, right? And how do the super martingales support the variance? Well, you just require the variance to be bounded within sub-level sets of the super martingale. In a sense, you just require the variance to be bounded while the super martingale itself is bounded. Okay? So this is the proof rule that we proposed last year. Can we just use this proof rule directly to prove the termination of consensus algorithms? Well, again, not quite, because consensus algorithms like Benor assume fairness constraints, assume fairness. And the place where fairness affects the proof rule is in the variance. You see, the variants require a reduction with a minimum probability at each step, no matter how the non-determinism is resolved. This is because the variants assume the worst case resolution of non-determinism, which in the case of consensus algorithms can be unfair. For example, processes can be ignored forever, or Byzantine processes can be scheduled continuously after some point, or some messages that were sent to the network would never actually be delivered. And we have to augment or modify variants so that they actually account for fairness. Well, how do we do this? Well, let's start with something a bit simpler. Let's take this program that we've seen earlier, and let's augment it a tiny bit. Now there is a non-deterministic choice where you could either reduce x or with probability half, or do nothing. You can choose to do nothing if you want to, non-deterministically. So this program will terminate if you assume fairness. Fairness here means that both directions, non-deterministically, are taken infinitely often. And the only way you will not terminate is if you keep taking skip the second direction infinitely often. So in a sense, the first direction is helpful toward termination, while the second direction is not, right? So this idea of a helpful direction toward termination was formally noted by Francis in 1986, where essentially to prove fair termination of non-deterministic, non-probabilistic programs, you find a helpful direction function that is enabled is enabled whenever that essentially tells you which direction to take to reduce the variant. And how does this work? Well, okay, yeah, right. In this particular example, the helpful direction is obviously just the first direction, right? So how do we modify variants so that they work with the helpful directions? Well, you kind of just need to reduce the variant whenever a helpful direction is taken and keep the variant the same, or at least not increase the variant otherwise. This is our new proof rule for showing almost sure termination under fairness constraints, and we will use this to prove the termination of Benor. So how do we do this? Well, remember these two theorems. To codify this, let's make a definition. Let G represent the total number of steps of Benor in a single round across all processes. Note that in the first theorem just says if all non-faulty process, first theorem just requires one round of execution to terminate. This requires G steps. The second theorem requires 2 G steps because the lucky sequence spans 2 rounds. So the variant, which is still some idea of a length of a terminating run, from the initial state will be 2G plus G. And is this enough? Well, not really, because the second theorem requires the lucky sequence of coin tosses to happen. What if the coin tosses are not so lucky? So to be able to do that, let's track that. Let's add a variable tracking the number of unlucky coin toss sequences so far. And each time a coin toss sequence is unlucky, you have to try it again. So that adds another f times 2g to the variant. And finally, just reduce the number of steps completed so far. And this gives us a probabilistic variant for Benor's algorithm. Now, in interests of time, I will not go into too much detail about the other certificates here. We can show that this particular super martingale works for the variant. And importantly, this particular choice of helpful directions will work. Essentially, choosing any non-deterministic choice that changes the local state is enough to ensure that this value, R over here, reduces. Okay? Now, we have, in our paper, validated these certificates for Benor using Caesar, the verification infrastructure that I mentioned earlier. And I'd like you to note the exponentials in the super martingale. This means that the super martingale is outside the reach of existing template-based methods to prove the almost sure termination of probabilistic programs. Okay? Now, to summarize, in our work, we have machine-checked the almost sure termination of an elegant randomized protocol for distributed consensus using a new general proof rule for deducing the almost sure termination of non-deterministic probabilistic programs under fairness constraints that can potentially be applied to other distributed algorithms to prove their termination. In the paper, we have machine-checked termination proofs for a general class of efficient consensus algorithms tolerating crash and Byzantine faults. As future work, we would like to take a look at, we plan to take a look at harder fairness assumptions and algorithms with weaker guarantees and algorithms that incorporate cryptographic reasoning. Thank you for listening. I'm happy to take questions.
Questions?
So when you were describing your fairness assumptions, you said all messages are eventually delivered. Mm-hmm. It's a pretty strong assumption, right? So you don't allow any message to be dropped? Or did you mean that you're going to have like infinite retries?
We just assume very little about the network. It could potentially happen that a message is delivered after many, many retries, yeah. But well, these algorithms were proven correct under these fairness assumptions, so we just took these fairness assumptions and just wrote them down, yeah.
So down here,
Oh, sorry. Yeah.
So a common way of dealing with the fairness assumption is to assume like a partial synchrony model where eventually, right, the system goes into a state in which everything is fair. I've been trying to connect what you're doing to that model, which I think is a more standard way of doing this. So can you just relate that a little bit?
Sure. Partial synchrony, in a sense, kind of deals with something that is also called finite-ary fairness, I think, in the literature. This was introduced, I think, by Rajiv Allur and Hensinger a couple of years back. So in partial synchrony, you just say there is some bound such that messages are always delivered under this bound. Or let's say sometime in the future there is global across all messages, you see. That's the entire point. There is some bound, is the entire point. But here we just assume that there is no, let's say, upper bound on a simple global execution of how much time it takes for a message to be delivered. So this is the kind of the difference between the two. I believe with partial synchrony, the proof rule can become a bit simpler, but blanking at the moment, I'm sorry.
I have a somewhat speculative question. So in the non-probabilistic setting, fair termination, non-termination is often seen as a representative problem, and then you can do many other things once you solve this. So is there a hope to kind of have a more gentle class of problems that you can solve in this setting, like defining some language like LTL or something?
Yeah, I mean, yes, I think that would be something that we would like to do. But for that, I think the best way to do that, this proof rule can already solve any of these kinds of consensus protocols or any distributed protocols for which the proof rules can apply. But we have no completeness results. That's the bottleneck at the moment. If we had completeness results, we can solve a general class, any kind of general class of problems with these proof rules.
Okay, so let's thank the speaker once again. Okay, so on to our next talk, which will be presented by Clément Alain on Zoo, a framework for the verification of concurrent OCaml5 programs using separation logic.
Can you hear me? Is it okay? So, hi everyone, my name is Clément Alain. This is joint work with Gabriel Scherer. It's my pleasure today to present this work in a very impressive place. This is basically the result of my PhD. So the story is the following. At the start of my PhD in 2022, the fifth version of the OCaml programming language was released, OCaml5, in December 2022, to be more precise. And well, this version introduced parallelism and concurrency into the language through a number of new mechanisms. And then, reacting to that, the OCaml ecosystem developed a number of new concurrent in parallel libraries, including domain sleep library, which provides a standard scheduler for OCaml, the Saturn library, which provides standard log-free algorithms, and also, among others, the EIO library, which provides an, support for asynchronous I/O. And, well, obviously, given this new software, new tricky concurrent algorithms, we need to apply formal verification, obviously. So this is the motivation. Our motivation is to this work, verify real-life algorithms using state-of-the-art techniques. And, well, at the start of my PhD, the most natural things to do was to use the heap-lang language. So this is the canonical Iris language. It's mechanized like Iris. So by the way, Iris is, some of you may know, is a very powerful separation logic. I claim that it is basically necessary to verify the kind of algorithm that I want to verify. So for me, it's like a constraint. So I needed a language that supports Iris. So heap-lang was the natural choice. However, our experience shows that it is, well, a bit limited when it comes to verifying real-life OCaml programs at scale. So basically, this is the starting point of our work based on the fact that the abstractions in heap-lang and also some incompatibilities that I will talk about were not ideal for verifying the programs that we wanted to verify. So we developed the Zoo framework for verifying concurrent OCaml programs, and now I'd like to give a brief overview of this framework. So the idea is the following. Say you have some OCaml code, say you have a June project, and you want to verify the libraries in this June project, so you can call this tool OCaml'26, and well, it's actually a transpiler. It will translate the files, the OCaml files, basically the project, into rock files containing Zoo code, which is a language deeply embedded inside rock, and then you can use the Iris separation logic. Now, concretely, so you have this June project. Say you are implementing the domains lib library, so scheduler, a parallel scheduler, and this domains lib library relies on the Saturn library. Then calling OCaml'26 on this project yields the following hierarchy. So basically, for each ML file, you generate corresponding rock files, one for the Zoo codes, one for the Zoo representation of the OCaml types. Actually, Zoo, like heap-lang, is an untyped language. It's untyped because we need to deal with unsafe features, and basically we can't be typed. Now, zooming on the stack module. So actually, the stack module implements a concurrent stack. Great. So actually, it's the triple stack that Alexander has already mentioned and already presented. So the idea is that you have an atomic reference and you update it using component set. So for instance, here you have the push function. This is the OCaml code, and calling OCaml'26 yields the following Zoo code. Overall, it's pretty similar to the original code. I hope you will agree with me. Some little differences are due, I would say, to the current state of language and embedding inside rock. So anyway, the code in particular is pretty readable, so it can be reviewed to check for the consistency of the generated code. And so then, to show how you verify programs in practice, once you've entered the rock world, well, the real work starts. That's when you want to write specifications first. So, for instance, this is the way you would, the standard way you would specify the push function for the tribal stack. And well, this is, again, like Alexander mentioned in this talk, in his talk, this is a so-called atomic specification, iris atomic specification. So basically what you're saying here is that you are logically updating the stack from VS, some value VS that you get at the linearization points of this function. You're updating the stack from VS to VS plus V. So basically you're atomically pushing value V. And this is more or less equivalent to showing that this push operation is linearizable as is standard in the literature. Okay, so now to wrap up this global overview, here are the features currently supported by Zoo. In particular, note that you have the high-level abstractions like ADTs, records, and mutually recursive functions. Those things are not supported by heap-length. This is the kind of things that brought me into developing Zoo. And also, it supports physical equality. I will talk more about that in a few minutes. Also, another part of this work, I would say, is contributions to the OCaml language itself. So indeed, with Gabriel Scherer, we developed a number of new OCaml abstractions, OCaml features. So atomic references are already there in OCaml 5. We added atomic record fields. I will show what it looks like in a few minutes. Atomic arrays and also so-called generative constructors that I will also present soon. Okay. Now, here, I don't have time to go into much detail, but I would at least try to convince you that this framework is practical. I hope it is. So here are a few things that we've verified, a few verification contributions, we said. So inside Rock is the Zoo framework. Inside Zoo, we verified standard data structure, so more or less a subset of the OCaml's stdlib. So in particular, some sequential and also some concurrent modules. And then we've also added some here in pink. Then we've also verified persistent data structures, in particular arrays, stores, and union-find algorithms. And here I would like to thank Basile Clément and Gabriel Scherer for developing the persistent store library and suggesting me to verify it. Also, we verified the RC of the module, which is basically a parallelism-safe file descriptor that I will also present in more detail. And I would like to also thank Thomas Leonard for developing this, EIO and in particular this module. This RCFD module comes from the EIO library. It is interesting in several respects. So actually, Thomas Leonard suggesting verifying this data structure because of its quite intricate concurrent protocol. But as we'll see, it is also interesting, so we found, for introducing, for justifying generative constructors. Last but not least, we also verified a library of standard log-free data structures. Again, I would like to warmly thank Vesa Karvonen and Karin Morel, the two developers of the Saturn libraries. The Saturn libraries. This algorithm comes from the Saturn library. So In particular, we verified, so actually we've not verified all algorithms, it's future work. We verified stacks, queues, different kind of queues, lists, array, and stack based. Okay, so this was the overview of Zoo and the different contributions we've made. Now for the time I have left, I would like to focus on a subtle aspect that we've worked on. So physical equality. If you program in a camel, you may already be familiar with this. So in a camel, this would be the equal operator, physical equality. And the question is, why am I talking about physical equality? So I claim that physical equality is ubiquitous in concurrent programs. Why is that? Well, again, consider the tribal stack, an atomic reference pointing to a list, an immutable list. When you create the stack, this is an empty list, and then you want to, in the push function, you want to atomically update this atomic reference, using the atomic primitive comparent set. Okay. So you read the reference, you read the content, you construct the new list that you want to update the reference to, and then you try. You try to atomically update it using the comparison primitive. And well, if it works, you're good to go. Otherwise, you start over. Okay. So physical equality lies here in the atomic comparison set primitive. Why is that? Well, because you don't want to apply structural equality. It's too slow. So you want a fast test, a fast check to see, to compute whether you've seen the same content. Okay. So now I claim that in OCaml, so we have found in our work during the verification of, in particular this algorithm, but others also, we found that it is underspecified in OCaml. In particular, I claim that the current documentation is not sufficient for, it's not precise enough for verifying this standard simple data structure, the tribal stack. Also, in heaplang, the formalization, the way physical equality is handled is basically incompatible with OCaml. So in particular, it is too restrictive. For instance, you cannot write this data structure as it is. And so the question is, can we do better? And the answer is yes. And so we present a new formalization of physical equality that we hope will influence the way it is documented in OCaml. So now let's see what can go wrong. So first, let's study the case when physical equality returns true. So when it returns true in this precise algorithm, in the tribal stack, so the most important point is the comparison set call. So say, you have the invariant of the stack, and what you want to do is atomically update the content, so VS. So atomically, you observe some values VS, and this is the current content of the stack. Okay. You call comparison set, and in the branch that is interesting here, in the branch where physical equality, which lies underneath comparison set, returns true. What you know in OCaml is that not only you have actually updated atomically the content of the stack, but also you've seen the VS, the values that you've observed, is physically similar to the old values that you observed in the first place. Okay, so this looks good. But then what you really want to say is that given that, you can have this. So you want to say that old and VS are actually the same thing, so that in the end you get the standard specification. The question is it true? Well, it appears that it's not. And to see why, we have to consider several phenomena. So first, sharing. So this is a standard thing in OCaml. Basically, immutable blocks, including count cells, are represented in memory as immutable blocks. And basically, the compiler and the runtime, for instance, through hash counting, might or might not choose to share these blocks. So sharing means basically giving the same actual memory block to some abstract immutable block. Okay, so this means that in OCaml, you may observe, as shown by these two tests, you may observe either true or false when you test equality of two syntactically similar lists. So you don't have that equality in rock over the abstract representation of values, particularly the immutable blocks. You don't have that equality in rock implies physical equality in OCaml. Now, this is quite standard. The big problem comes when you consider also value representation conflicts. So usually when you program in OCaml, you cannot observe these conflicts. Why? Because you're typed. The program is typed. So for instance, you cannot compare false and zero. You cannot compare booleans with integers. Except you can sometimes. You can, for instance, through this any type, which is basically an existential type. And basically this type, this any constructor in particular, so this immutable block, hides, basically erases the type. So when you call physical equality, this double equal comparator, things happen. So in particular, what the compiler sees is actually the physical representation of false and zero, which is actually the same thing. And so through sharing and these conflicts, you may get, if sharing is enabled, true for all these tests. So this means that physical equality in OCaml, in OCaml, physical equality in OCaml does not imply equality in rock. You don't get that the abstract value that you have in the verification, in the verified program are actually the same. So you cannot deduce that old and VS are actually the same. And so all you can do, given this behavior, this phenomena, is verify a more imprecise specification, basically a specification modulo, where you reason modulo physical equality. You only update the stack with a value that is physically similar to the former values. Okay, so this is the case when physical equality returns false. Now, the case when physical equality returns, this was the case when physical equality returned true. Now, in the case where physical equality returns false, this is also interesting. So actually, if you look in the OCaml documentation, you can read that basically in this case, you get no guarantee. No guarantee. And I would like to show in this second example that this is a problem in practice, including for functional correctness. So here is an extract from the code of the RCFD module that I've mentioned. So the parallelism safe file descriptor implemented by Thomas Leonard. What happens here first is that we're using our atomic record fields, the fields that we've introduced in this work. So this takes the form of this atomic annotation. Here you're declaring this field as atomic, and then you want to atomically update the state fields using the new atomic.lock primitive that mirror the standard atomic primitives. And also we have a construction to this atomic.lock construction to actually get the field and then have a type have a nice type for the comparison set primitive. Anyway, so I claim that okay. First of all, I should briefly say what the story of this data structure is. So basically, what happens here is that we have a state type, state ADT, and this says that the state is either open or closing. Okay, either open and closing, and so at the start it's open, and then it gets closed. You switch to closing, and it's the end. You only get closing afterwards. And then I claim very briefly that what happens is that in the case where physicality returns false, you have a problem because you want to argue that you have observed a closed descriptor, although it is not because of a particular phenomenon that is unsharing, which is a theoretical concern, but also, according to experts, may really happen in practice. So now, briefly to wrap up, first we have introduced generative constructors to handle all these problems. I don't have time to describe it, but it's in the paper. And to conclude, here are a few ideas for future work. More features, also coupling with semi-automated verification and relaxed memory. I don't have time, but thank you.
So we have time for one quick question. So have you tried applying these techniques to other languages, or is it very focused on OCaml?
It's very focused on OCaml, and this kind of, this is like surgery. We've looked deeply like what does this precise notion, physicality, means in OCaml. It will be a bit bold to speak about other languages. I guess that in other languages where, in garbage collected Java, say, languages where you have immutable values, this may also happen.
Let's thank the speaker again. Do you want to go to display and see? So the last talk of the session will be by Umang Mathur, and it's on the complexity of testing message passing concurrency.
Unfortunately could not travel. Together with Lasse and Andreas, who are at the University of at Aarhus University. And this work stems from our desire to improve the state of the art in program analysis for a language like Go, where message passing communication is a sort of key mode of communication across Go routines. And let me sort of do the routine pitch for why do I care about this problem. Well, because no matter what software application you pick, it's very likely built using concurrency in mind. And in fact, if you talk about modern AI revolution, it would not be an overstatement if I say that it's partly because of concurrency-centric advances in both in hardware and software. But at the same time, we have to acknowledge that developing concurrent software is not an easy task, primarily because if you really go and reason about all interleavings, that's a very large space of interleavings. And for this very reason, many concurrency bugs escape into production level software, and that's not ideal. So one of the popular ways of analyzing programs or concurrent programs so that you can minimize some of these errors is through variants of what I call dynamic analysis or dynamic program analysis, where essentially you look at one or many executions from your program and then sort of do some sort of lightweight testing based on that. And two of my favorite dynamic program analysis for concurrent software are predictive analysis and model checking. So let me first tell you what predictive analysis is. Here you look at your program and you, with the hope of analyzing an execution, you execute the program, and then perhaps you may not find a bug right away, but you can perhaps try to also reason about possible other interleavings that you can infer from this particular execution, and in doing so, you may be able to find a bug. And this is essentially the essence of predictive analysis. Model checking is also sort of similar in a very broad sense. You have a program and you explore all the executions of the program, let's say up to bound. And these days, modern model checkers are sort of smart in the sense that they don't really explore every possible interleaving. They allow you to do some optimization, and the most famous one is the deep OR optimization or partial order reduction based optimization, where you only execute one execution per equivalence class. So the black lines are those interleavings, and implicitly you essentially also get the guarantee for the entire equivalence class, the green region. So why am I talking about these two in particular? I mean, of course, they are my favorite, but also because the core problem that you end up solving when designing such analysis is the consistency problem, and that's what this work is about. So, if you haven't yet gotten a hang of, predictive analysis, let me sort of run you through yet another example. So here I have a Go program, and it is a bit problematic because over here I have two Go routines, and they're talking on a common channel, and one of the Go routines has the ability to close the channel. And as such, if you've written many Go programs, you would see that this is not really a nice program, because if you're under some bad interleaving, you may actually end up closing the channel before the other Go routine accesses it. So as a developer, I may be interested in finding these kinds of bugs. And let's say my go-to technique is dynamic analysis, where I draw an execution from the program and look at it. So let's say this is the execution that I got out of it. And here, unfortunately, because my testing is not so thorough, I actually got a very nice execution. It's not buggy. Here, the close of the channel happens way at the end, so it doesn't really expose a problem. But if you pay attention to it, you can actually reason about the problem anyway, because you can say that, well, if I look at this execution, I can actually reorder the send event on thread T2 all the way to the end, and this hypothetical reordering is actually bad because it will raise a panic in my Go program because it's accessing the channel after the channel is closed. Okay, so that's essentially how predictive analysis works. And as I said, the core question that comes up in all such analysis is the consistency question. So if I have to reason about these kinds of interleavings and ask about is there another interleaving, blah, 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 then I have to be very careful because it's not like all permutations of the observed execution are actually going to be valid. There are going to be constraints that one must satisfy so as to ensure that the interleaving that you're thinking about is really an interleaving of the same program that gave you the execution in the beginning. Now, with that in mind, one can actually phrase this as a computational problem. And the computational problem can be sort of very succinctly described as follows. To begin with, you take your execution and you sort of let go of some serialization orders, and you retain the very core essence of that execution. I call that a partial execution. It talks about what are the set of events in that execution, together with, let's say, what is the order between events of the same thread and other kinds of dependencies that must be respected in all other interleavings. And together with that, you also have to talk about the communication paradigm. In this case, the paradigm is channel-based communication. So the key question that you end up asking is, I'm given this partial execution, and I'm interested in checking if there is a total order of this total order extension of this partial execution, which is also communication safe in the sense that it will indeed be executed by a valid Go program. In fact, the very same program that gave me the very first execution. Okay? So in all these analyses, this is indeed the key computational question that you end up solving. And in this work, we essentially take a thorough complexity theoretic investigation about this problem. So we're looking at the problem of checking channel consistency. I have sort of roughly told you what this is about, and in the coming slides I will go in much more detail because the audience may not have a lot of background over here. And we studied two variants of this problem. One is the channel consistency verification and the channel consistency verification under reads from mapping. So these are the two variants of the question that make much sense in the kinds of applications that one typically looks at in concurrent program analysis. And in this paper, we sort of look at this problem from a computational lens, and we identify how difficult is this problem, and we sort of state some lower bounds on solving this problem. We also come up with upper bounds, which in some sense are actually very optimal. They're matching upper bounds. And we also evaluate our algorithms and test if they really would fare okay in practice. Okay, so with that in mind, let's go through things a little bit slowly. So if you think you may already know this space, it's a good time to go to sleep. I'll wake you up in 5 minutes. Okay, so what is the setup? The setup is you're given a partial execution. So let me first define what that is. So a partial execution is this sort of a tuple. It talks about a set S of events. Events can be one of sends or receive events. So each event is of this kind. It tells you what is the thread that performs that event. So T is the thread over here, together with what is the operation that was performed in that event. See, so operation can be one of send or receive in this case. And there's additional information about the channel identifier, CH, over there. And finally, you also talk about what is the value being sent or received in that channel. So in some sense, this is essentially capturing whatever you really require to talk about to detect bugs. On top of that, in this particular setting, and more in the context of Go, Go has this peculiarity that it allows for channels which may have capacity which is not 0 or not 1, but maybe a finite capacity or sometimes even infinite capacity. And finally, you also talk about what is the program order on this set of events. So this is something that you would have to respect when you're talking about possible interleavings. So this is your input. A slight variant of this input is the reads from setup, where you're additionally also given a reads from mapping. In this case, reads from mapping basically means for every receive event, what is the corresponding send event that it is receiving from? Okay, so that's the kind of inputs to my algorithmic problem. And some terminology over here, if I have a channel, then I call it a synchronous channel if its capacity is 0. So a language like Go allows you to communicate through synchronous channels, where the semantics is that if I decide to send over a synchronous channel, then the receiver must immediately be available. Likewise, channels are asynchronous if, or non-blocking, if you can sort of send multiple messages. You can send one or more messages and sort of move on. And finally, Go also allows you to have channels of unbounded capacity. All right, so that was part of the input. Let's also now talk about what are the kinds of things that we're looking for. So we're looking for an interleaving of those sets of events. So let's talk about interleavings. So an interleaving sigma of n events is a completion of the partial execution that I just talked about. If number one, it's a serialization of the set S. So S is equal to the set even through En. This total order also respects the program order. And finally, it also respects the reads from mapping, if that is also part of your input. By that I mean, if I look at the ith send and if I look at the ith receive, they are indeed those that my input asks for. Okay, so now it's a good time to talk about what is the problem statement. So the problem statement is to check for channel consistency. So you're given a, okay, so maybe let me sort of rephrase it as a consistency condition. So you're given a total order, and the total order satisfies channel consistency if it basically does not, if it continues to obey the FIFO semantics of channels. So that means that if I look at the ith receive, then its value is the same as that of the ith send. That happens for every channel. And because channels may have capacities, you also have to sort of say that if I have a synchronous channel, then every send of that channel is immediately followed by a receive. And you cannot have unmatched sends. And finally, if I have a channel of capacity, let's say 5, then I also require that at any given point in the total order, if you look at the channel, you cannot have more than, let's say, 5 events. And you have to have it. You have to have more sends than receives. So that's sort of roughly mathematically capturing the intuition of FIFO semantics. All right. So now is a good time to talk about the problem statement, which is that you're given a partial execution, and you have to report if there is a completion of the partial execution that is also channel consistent. And the reads from variant of this problem is, this time you're given a partial execution that also talks about the reads from mapping that you must obey. And you have to report if there is a total order extension of this partial execution which satisfies the channel consistency conditions. Okay, so it took me a long while to get here, but now you can wake up. Okay, so let's now talk about the key results of the paper, and much of the paper is really about complexity in algorithms, so I will also try to focus on those parts. Towards the end, I will also talk a little bit about how the algorithms that we develop also fare in practice. All right, so remember our input is of that kind. Our complexity results are going to be stated in some of the parameters of the input. So the parameters are the number of events n, how many threads you have, T, that turns out to be a very good parameter to talk about, the number of channels, M, and also what is the largest capacity of the channels that you have. So, you know, for the experts over here, it would not be a surprise if I tell you that this problem of consistency checking is actually NP-hard. But the interesting part is that it's NP-hard in sort of very surprising ways, something that you would not see in the case of registers, where shared memory-based communication. So we actually we show that in each of these cases, the problem continues to be hard. So single value basically means that all channels are communicating only a single value. So even that degenerate case is also very difficult for channels. So on the other end, we have algorithms that are of this kind. They work in time complexity n raised to t multiplied by t raised to km. And if you sort of pay attention to it, it's actually a better algorithm than something that, you know, that iterates over all permutations, because that would take, I think, something around t raised to n time. So n raised to t is better than t raised to n because the number of threads is typically much smaller than the length of the execution itself. For the dual problem of read-from consistency, unsurprisingly, we also have NP hardness, and this also the interactability continues to hold in pretty degenerate cases as well. And some of these are sort of surprising if you think about the shared memory version of this problem. And on the other end, we have upper bounds, which are slightly better than the harder problem of VCH without the reads from. And then we also look at some other interesting cases which we think do arise in practice. One of them is acyclic topology and the case where every channel is synchronous. So I do have some time, right? Okay. All right. So let me talk about where does the difficulty really come from. The very first observation that I'd like to make is that this problem, VCH, is actually harder than the corresponding problem when you have, you know, registers. And that's because you can actually simulate registers using channels, in fact, channels of capacity 1. So roughly the construction goes as follows. You sort of, for every write event, you translate it into a bunch of, you know, sends and receive events. It basically says that you have to do many sends, and then you have to do some amount of receives, so that when I see later read events on this channel, I will be able to sort of to dequeue the channels and things work out. So you don't need to worry about it. So the bottom line is that this problem is harder than the case of registers. But what's interesting is that for a much simpler case where the problem is actually very easily solvable for registers, namely when you're given an instance and every value is the same. Imagine if you're given such an instance in the case of registers, you can pretty much in linear time, I mean, I would think constant time, determine if that is indeed a consistent instance. The only time it won't be consistent is if there is no write, otherwise it's always consistent. So it's like an order 1 algorithm. But when you have channels, you can do many fancy things. You can basically sort of, you essentially have access to a tape, like a Turing machine. And for that reason, you can actually simulate the Hamiltonian path problem. I don't think I have the time to go through the reduction, but it's pretty cute, so you should go and check out the paper. Let's also talk about the algorithm for VCH. As such, if you've looked at consistency problems before, this algorithm that we have has a very similar flavor to what is generally called as a frontier graph algorithm. And remember, the goal of the algorithm is to come up with a complexity of the kind n raised to t and not t raised to n. So if you think about it, n raised to t you would get because you're trying to enumerate all possible sets of events which are downward closed with respect to program order. And the number of such sets is approximately of the order of n raised to t. So I'll probably very briefly skim through what this algorithm really does. So it essentially constructs a graph on these downward closed sets. Each of the nodes in this graph is called a frontier, and you can think of a frontier as some sort of an abstraction of a partial execution. So each such node talks about how many events have been executed in each thread, and also for every channel, what are the contents of that channel, and extra information around that. So I don't think I have the time to go through the details over here. And on top of that, you can also talk about how I can extend one frontier to a slightly larger frontier using an event, basically by adding an event in that set of the events. And there are conditions on when such an addition is allowed. And the conditions basically says that, you really need to respect how channels behave. And together, we have a graph which is such that if I look at that graph, then every path in that graph by construction is such that it is indeed a consistent total order of my partial execution. And for that reason, and in fact, every consistent total order is also a path in that graph. And for that reason, the VCH problem can indeed be solved in time that is proportional to how much time you would take to construct the graph and to also run reachability on this graph. And that turns out to be something of the order of n raised to t multiplied by t raised to km. Remember, k was the number of channels, k was the largest capacity of a channel, and m was the number of channels. Okay, so I will very briefly skim through what is this other result that we have. It is about communication topologies, and it talks about a subclass of instances where you can actually solve this problem in quadratic time. So you sort of characterize these instances by looking at how threads communicate with each other, and then you come up with the notion of graph on threads. And if that graph turns out to be acyclic, then it turns out that you can solve this problem in quadratic time, thanks to a very nice compositionality lemma, which says that in such a case, you can actually decompose this problem into pairwise threads and solve each of these problems in pretty much linear time, in quadratic time, and therefore in total also you can solve the whole problem in quadratic time. All right, so now let me sort of walk you through the highlights of our evaluation. How did we do the evaluation? So what do we need for our evaluation? We need benchmarks that can give us these instances. The way we go about this is by collecting all the popular Go software and logging executions from using thread sanitizer and extracting these instances out of it. So these would mostly be positive instances, and we do some surgery to also get negative instances. So it turns out that if you compare it against a vanilla algorithm using SMT solving, because you can encode a lot of these constraints as a SMT formula, you are of course going to be much better than something as naive as that, because these executions can typically be millions of events. So yeah, we do very well as compared to SMT solving. But we took a closer look, and we identified that actually we're also not that good. And it turns out that if you do a better heuristic on top of the algorithm, which is called saturation, you can actually do amazing. So at the end, you sort of end up solving all these instances in reasonable time. So I think with that, I'd like to summarize. I've talked about what is the channel consistency problem, and I've talked about our contributions. We sort of primarily look at this problem from a complexity theoretic lens and show that this is a hard problem even for very simple cases. And then we also come up with matching lower bounds, and we demonstrate the matching upper bounds, and we demonstrate the power of these algorithms through pretty much extensive evaluation. So with that, I'd like to end the presentation.
We are basically out of time, but maybe one quick question. If not, maybe we just thank the speaker once again.
It's 2 p.m. I think we will start on time. So welcome to this session on proof assistance. It's one of two such sessions in POPL, and arguably many more papers could be labeled by the label proof assistance, fortunately at POPL. But in this session, we have 4 talks that not only use proof assistance, but they also study meta-theoretic properties of proof assistance or extend proof assistance with new features, and also formally verify these extensions. So the first talk will be given by Nathaniel Courant and is co-authored by Xavier Leroy, and it will be about a lazy concurrent convertibility checker.
So, thank you for the introduction. So, I'm Nathaniel Courant. I currently work at POPL', but what I will tell you about today is what I did during my PhD with Xavier Leroy at INRIA about building a lazy concurrent convertibility checker. So, a convertibility checker tries to prove that two things are equal and is critical when writing a proof assistant with dependent types. So, as motivation, let us consider f be an expensive function to compute. And we want to efficiently prove that f of 20 is convertible with f of 20. This problem is easy. Both sides are identical, but we already see that reducing both sides to normal form, the naive version will be inefficient. Let us consider another problem where we have two different free variables on both sides, and we have x of f of 20 on one side, on y on another side. These two terms are not convertible, and again, we need to evaluate f of 20 lazily if we want to prove that efficiently. Suppose now we want to prove that f of 20 is convertible with f of 19 plus 1. So we will use we can prove this efficiently just by proving that 20 is convertible with 19 plus 1. And this is the strategy used by Rock and many other theorem provers to try to prove the convertibility of the arguments first before expanding the function. However, this strategy has drawbacks. So consider for now the k combinator, which returns its first argument, and suppose that we have on one side k of 0 on f of 20, on the other side k of 0 on f of 21. If we try to prove the convertibility of the arguments first, we will perform a very expensive computation, whereas if we unfold k first and compare both sides, we can prove convertibility very efficiently. Sometimes we have two different head constants on both sides, and it's unclear which we need to unfold. So again, Rock uses heuristics to do this. But suppose that here f is the exponential function, and we want to prove that f of 20 is convertible to f of 19 plus f of 19. If we unfold f on the left-hand side, but not plus on the right-hand side, we can prove convertibility very efficiently by noticing that after that we have identical sides. However, if we want to prove that f of 20 is convertible with 0 plus f of 20, with the same head constants on both sides, but different arguments, here we need to unfold plus, and then we can obtain identical sides and prove convertibility. So it's very difficult to know which would be the good option without effectively trying it. So the formal statement of the problem is that we have a lambda calculus with defined constants. So for instance, f or k in the previous examples, which are associated to a term. We have two operations, beta reduction as usual, and delta reduction, which replaces a constant by its definition. The convertibility test is just to, we want to ask whether two terms are beta-delta equivalent. In the paper, we handle eta as well, but I won't talk about it here. And we make the hypothesis that we have only strongly normalizing terms for decidability, which is the case in proof assistance such as ROC. But we don't use typing information at all to write our convertibility test. So the textbook way to test convertibility is to reduce both sides to normal forms and check whether the normal forms are equal. In the presence of strongly normalizing terms, this shows decidability, but it's very inefficient. The standard way, the one used by most theorem provers, is to reduce to weak head normal forms both sides, look if those sides have the same shape, and if they do, we have several other convertibility tests to solve again, which we do recursively. This is efficient if the right unfolding decisions are taken as I showed in the introduction, but it can be costly otherwise. For the large theorem provers, the important ones, they use a heuristics to guide unfolding, which are not always successful. So what our proposal is instead to have a concurrent execution of both convertibility tests and evaluation steps, everything computing concurrently, and try to find solutions as early as possible. So for that, we start by expressing laziness as a process calculus. So we have an infinite set of channels, alpha, beta, and so on, and processes which can reduce a given term m to a value and send it on a given channel alpha. They can be any term, and they may use alpha question mark to read a value from alpha and continue once the process on alpha has finished computing it, has finished computing a value and continue with that value. We can execute processes concurrently and we can generate fresh channel names. The most important rule is the communication rule, where if we have a process waiting on a value on alpha and another process which has finished computing a value on alpha, then the first process receives the value and we keep the other process in case other processes ask again for a value on alpha. This can be used to represent non-strict evaluation, where a lazy value is simply a channel name. Creating a new lazy value, to create a new lazy value, we create a process which evaluates the term and sends it to a channel, the channel which represents the lazy value, and forcing the value is simply waiting for a value on that channel. So nothing in that enforces real laziness. We only have non-strict evaluation. The lazy part comes from the scheduler, which will not reduce m in alpha bang m until alpha is itself forced. So until some other thread is waiting for a value on alpha. And with these notations, so we can write a convertibility test between two terms, T1 and T2, as a convertibility process, conv, which asks for two weak head normal forms, which it will receive on channels beta and gamma, and two processes, eval, which reduce the values to weak head normal form and send these results. We also have a mapping between three variables of both terms, as usual, to deal with binders. So what do our weak head normal forms look like? The core idea is that we have a channel for lazy evaluation of function bodies and unfolded constants to avoid recomputing them repeatedly if we ask several times for either the function body of a closure or what happens when we unfold a head constant. So for a closure, we have the usual part, so the variable on the closure, an environment, and also this channel beta, which evaluates the body of the function with a new head variable, a new parameter. We have neutral terms for free variables, which is simply a free variable applied to a stack, a list of channels. And for constants, they look like free variables. So we have a given constant with a definition, a stack, and a channel which evaluates the result that happens after we unfold the constant. So we will first consider the concurrent convertibility test in the context of the pure lambda calculus. So if we want to compare two lambda terms, two functions, two closures, we simply need to compare the function bodies and extend the free variable mappings to say that both parameters should be considered the same. If, on the other hand, we have free variables on both sides, we simply compare the stacks and check that both head variables match. And in all other cases, since we don't consider eta in this talk, they are not convertible, so we can immediately conclude that we stop with a result of false. Comparing the stacks is where it gets interesting. So if only one stack is empty or both stacks are empty, it's either false or true. But if both stacks are non-empty, we generate two fresh convertibility tests, one for the head of the stack and one for the rest of the stack. And we combine them. And here we see this is done concurrently because the process on alpha is waiting for two other processes. So the two other processes will compute in parallel. And with short-circuiting semantics for here the AND Boolean operator, as soon as either process concludes with false, we will immediately conclude that both sides are not convertible without waiting for the rest of the computation to have finished. If we have constants, we have other rules as well. So if only one side is a constant, we don't really have a choice. We have to unfold it. But if both sides are different constants, we have a choice. And this is what I told in the introduction, that we don't know which one to unfold. So thus, the idea is to unfold both in parallel. So on one side, we unfold the left constant. On the other side, we unfold the right constant. And we do this concurrently. And we know that both unfoldings will give the same result in terms of convertibility of the argument of both sides. So we have this choice operator where A choice B is B, assuming that A equals B. This is not a normal Boolean operator because it's not interesting. If seen as a Boolean operator,
But if we look at it in terms of computation, this is an operator which short circuits as soon as either side is computed and stops with this result. And finally, the most interesting case is if both heads are the same constant. In that case, we can unfold either, but we can also compare the stacks and see if they match. If they do, we know that both sides are convertible, but if they don't, we have no information. So we have this new operator biased choice here, where A biased choice B is B, assuming that A implies B. And this will short circuit if A evaluates to true, not false, sorry for the error, or when B is computed. So, with all these rules, we can prove convertibility efficiently, and we expressed what this efficiency means. So, we assume that we have a given set of rules to prove convertibility or non-convertibility of two terms. We give them in the paper, and we prove that the complexity of our algorithm is, on the worst case, exponential in the size of the shortest proof. This looks like a lot, but strategies with heuristics such as inside VOC cannot be bounded by any computable function of the shortest proof, so it's a very clear improvement. In practice, it's even better than that, because this worst case exponential happens only very rarely. And in practice, it's linear or almost linear. We have done a VOC formalization of the correctness of our algorithm. So we have proved the reduction rules which I have not shown, and the convertibility rules are correct with respect to beta and delta reduction. We have extensions to support constructors and shallow pattern matching, but we do not formalize the scheduling, so we do not have a formalized proof of complexity. All in all, the proof is about 10,000 lines, so it's moderately sized development. And it gives confidence in the correctness of our algorithm. We also do a lot of additional things in the paper, which you can look at. So we handle eta conversion. We avoid redundant unfolding of constants. So if you have two different constants on both sides, A on one side and B on the other side, with the algorithm I presented, we can unfold A, then B, and get some test, or unfold B, then A, and get another test. And with what I just presented there, I not shared, but we can avoid that. And we can even have additional sharing between identical source terms and between values that we encounter several times on both sides. We also present an explicit scheduling algorithm to show that it can be realized, which keeps a list of active processes. So active processes are those that are useful and needed for the evaluation to complete. And once a process becomes inactive, then we remove it from that list, or we add it to this list, depending on whether we need to execute it or not. So, in conclusion, we have a convertibility test for lambda terms with definitions and constructors in the Coq formalization, with worst time case time complexity bounds, depending only on the size of the shortest proof of convertibility or non-convertibility. It is formalized and verified in VOC, And in the future, we plan to extend it to other features of VOC, such as cofix points, universes, S-pop, and so on. We think we can get a bit better complexity bounds by improving the scheduling of processes. And we also want to produce proof traces and replay them to be even more efficient when checking the proofs. Thank you for your attention.
Thanks a lot for the talk. And are there any questions?
Do you believe the exponential optimality gap is optimal, or could there be an even tighter algorithm?
Not without changing the algorithm. We have some worst case examples where we are indeed exponential. So we would need to change the algorithm for that. But it seems like it doesn't happen so much in practice on the test we did.
Hi, thanks for the talk. This might be, it might be that I've just not internalized everything that's going on here, but does this algorithm split into sort of a purely non-deterministic but not concurrent algorithm, and then sort of a concurrent way of running a non-deterministic algorithm? It's like, can you see this algorithm purely as taking non-deterministic choices while evaluating things?
Yes, so the idea to replay proof traces is simply that when we have these short-circuiting operators, we could simply annotate them with the side that short-circuited, the side that computed. And if we want to replay a proof trace, we simply just ignore the side that did not short-circuit. And so this is the only non-deterministic part.
You retrieve the usual reduction, the usual convertibility test by the choice of an appropriate scheduler, or is it completely unrelated?
So yes, if you almost there's a bit of mutable state inside of Vox convertibility test. So this is not replicated, but for instance, in this choice, in these cases of having two head constants, the same head constant, if we only compute the left side here, and only if it fails compute the right side, we will get exactly the same thing as ROC does.
Yes. That's really cool work. So I was wondering, a lot of the actual conversion-like things that happen in kernels is more akin to unification. And do you think that basically the same ideas would also be applicable to a unification solver, or do you think they would need really something different there?
I've started to think about it, and I think it could be applicable, but it's not obvious because sometimes there are, depending on which branches you take, there may be several unification possibilities. So for instance, here you could prove convertibility of arguments with a given unification, but if you unfolded, you could see that this was not needed, and you didn't need to do that unification. So that I think there would be some additional ideas needed to conclude, to do something for that.
Thanks.
Okay, I think this will be the last question.
Great talk. So how does, can you prove that this algorithm is asymptotically more efficient than a breadth-first search of the derivation tree?
It's essentially a breadth-first search of the derivation tree, but so I've not talked about it much in this talk, but we need to share the computations on the different branches, And this is possible because of our process formalization, but without sharing, it would be a lot less efficient.
Okay, I think it's time to move on, and let's thank the speaker again. Next talk will be given by Andras Kovac, and it will be about proving canonicity for indexed inductive recursive types.
Currently, it doesn't show your screen. Yeah. Okay. Just a moment. Sorry, how can I mirror? Do you know? That's a good question. I don't actually know. Maybe this one should be the primary. It's here. As long as we can show it, we see it here, we will see it on the main screen afterward. Sorry, I don't know. How can I? Oh, replica off here. Okay.
One more computer scientist cannot help with
Yeah. I don't know. Sorry, can I try it again? Maybe if it just plug it. That one won't show anything, it's really. Is it showing that display's connected? Yeah, so there's this one. Extension? Sorry? Can you change it back to extension? Here rather than replica non. So replica non, yeah. Keep. Okay. Now we have the screen. Yeah, sorry. Be careful, it's going to show up this way. Yeah, you might have to move the window to that screen and present or something like that. Wait, it's still mirroring, it's not extending, right? No, you have to move the layout. So if you move that, like drag it to the side. Yeah. Oh, you might have to look at an arrangement first. So, that makes things.
Is he detecting a second monitor?
Yeah, so it's there,
Yeah,
but the two displays are like overlaid in the same space in X.
Sorry, what?
Like, I've seen this before.
So now we have this. Oh, hold on. Edit arrangement.
Yeah, we click that. Oh, okay. Okay, let's save it.
Okay, and then I apply it, and then keep.
Yeah, and then drag this to there.
Yeah, there you go.
And keep, and then drag this over. You're gonna have to grab the top of the window. So your mouse is on the other screen now. Okay, and then full screen and present.
Oh yeah.
Is that good?
Okay. Yeah. Sorry.
Okay, let's start. I'm András Kovács, and I'm going to talk about canonicity for indexed inductive recursive types. So, what are inductive recursive types? Here we can see a small Agda code example. So this is maybe the simplest interesting example for inductive recursive type. We define some data type, which we call code. So this is going to be a data type which contains codes for some types. And then we also have a function, EL, which computes a set from a code. And the idea is that we want to define some kind of small custom universe of types. And this universe only contains natural numbers. So you can see this not tick is a code for natural numbers. And then we have pytick, which is a code for a dependent function type. And this universe is kind of closed. So we also have an induction principle. So we can do reasoning on the codes in this universe by induction. And so early and informal use of induction recursion was first by Per Martin Löf. And then later in the 2000s, it was kind of made more rigorous by DB and Setzer. So there was essentially more formal syntax and semantics being developed. But let's do a more interesting example with induction recursion. So let's parameterize the previous definition with a set and also a family of sets over that thing and add some extra rules. So we still have code and we still have EL, but now we add a code for this U, which is now a parameter, and also we add codes for all elements of this family. And then we also do this extend the interpretation here. So we interpret U code with U, and we interpret EL code with EL. So what is happening here is that essentially whenever you have a type family, and this type family might be closed under some type formers, so you might think of it as some kind of universe. By induction recursion, we can define a bigger universe which contains a code for that family and the elements of that family. So we can think about this as an operator which makes a bigger universe from a smaller universe. So essentially you have this family of sets, and then by just defining this code and this EL, we get a function from families of sets to families of sets. And then we can iterate this function. So we can say that at 0, we have the empty family, and at successor, we have something which computes a bigger universe. So basically, this is a way of defining a countable hierarchy of universes by induction recursion. And we are still inside set. And we can also generalize this construction so that any well-founded universe hierarchy can be defined by induction recursion inside set. So this is essentially a convenient way of doing embedding universe hierarchies, and then also a convenient way of doing meta theory of universe features in some type theory. And there are some recent works on various notions of first-class universe levels, and all of these works use IR in Agda formalizations. So there's something about the consistency of first-class universe levels. There's another work by Chan and Weirik about canonicity. And then here at POPL, tomorrow there will be a presentation about normalization for first-class universe levels, which is pretty close to what is actually supported in Agda. And then some other uses, partial functions, generic programming, because you can do induction on these type universes, so you can do some generic functions. And then technically, so impredicative prop is a stronger feature in the proof theoretic sense, but we might still prefer to use induction recursion because we just like minimalism or we just like predicativity. And the formalization might be more convenient because IR definitions are really directly specify kind of the universe rules that we want. Okay, but what about the implementation and the meta theory of induction recursion? So it has been supported in Agda for a long time, also in Idris 1 and Idris 2. And informally, there's nothing special about the implementation. You just have a bunch of constructors, you have a bunch of functions, you just compute, and it just works. And no one really doubted that, that this is a good implementation. But of course, formally, it's much harder. So formally, we would like some syntactic properties of systems with induction recursion. So one is canonicity, which means that every closed term can be computed to a constructor, and normalization, which is that every open term can be computed to a normal form. And in this work, we show canonicity. Okay, so what is the basic setup? What is the object theory? And the object theory, we define the syntax by quotient inductive definition with some sorts. So we have typing contexts, we have types indexed over contexts, we have parallel substitutions indexed over the domain and codomain context, and then we have terms indexed over contexts and types. And of course, I didn't detail, but we have this explicit substitution calculus given as a category family. Countable universe is basic type formers and also inductive recursive types in every universe. And later, I will tell a bit more about how this is specified. But this is the basic setup. And the idea is that so we are using an algebraic presentation where we are only talking about well-typed terms, and we are also working up to definitional equality in every construction, which is convenient because we are not interested in untyped terms or properties which are kind of not stable under conversion. Okay, and what's the basic setup for the canonicity proof? So we use something which is called Artin gluing, and this is an established technique. It's a proof-relevant version of logical predicate interpretation, which works nicely for our setup. And the basic idea, we have the syntax, we do induction over the syntax, but because we have 4 sorts in the syntax, we get 4 mutual functions from this definition. So we have something which acts on context, and here we just get like, what is a canonical closed substitution? So by this dot, I mean an empty context. So this sub empty gamma is a closed substitution. And what we get from this function is really just a closed substitution is canonical if every term inside that is canonical. And it's a bit, for types, it's a bit more interesting because here for every type, assuming that we have a canonical closing substitution, we have to explain what it means to have a closed canonical term. So this function which goes from closed terms into set, this is the canonicity predicate that we have to define for every type former. And so for substitution, this is once again not so interesting. It's like a pointwise extension of term interpretation. But then for terms, it's this is again interesting because this is which is usually called the fundamental theorem or the fundamental lemma of logical predicate interpretations, where we have to say that whenever we have a term and we have a canonical closing substitution, then the result of doing the substitution also has to be canonical. But here we are already referring to the logical predicate interpretation of the type itself, because that's how we know what even canonicity is for this term. So, and this acts on every type and term former and respects definitional equality. Okay, let's focus on inductive types. So the main task in this interpretation is to specify what it means for a closed term to be canonical. And starting with a simple example, let's just assume natural numbers in the syntax of some type theory. So we have the type itself, we have 0, and then we have successor. And the closed canonical terms with this natural number type, we can specify them using an indexed inductive definition in the meta theory. So now this data definition, it's in the meta theory, and you can see that it is indexed over closed terms. And we just say that, well, 0 is a closed term, is a closed canonical term. And then whenever you have a closed canonical term, the successor of it is also a closed canonical term. So there is something generic going on here. And so the recipe in general is that whenever you have an inductive type in your object theory, you need to use something which has the same shape, but which is an indexed inductive definition in the meta theory. So this is the general recipe. Now let's try to do it for inductive recursive types. So what is the canonicity predicate for the code type that we saw as the first example? So let's just skip a bit. So just as a reminder, so we had this definition, and now we are interested in what it means to be a closed canonical term of type code. And this is what it means to be a closed canonical term of type code. So you can see here that we have an indexed inductive recursive type in the meta theory, which explains what it means to be a canonical term. So this is indexed over closed terms of type code. And then, for example, so we know that the code for natural numbers is canonical. That's OK. So that's described by this rule. But what do we want to say about having a closed canonical term which is of the form code for a function type? So we can see here that we have this contains a code, and then it contains a function which goes from ELA to code. So if we go to this definition, well, we need to have some term which is canonical, and then we need to have some term with a function type which is canonical. But then when are functions canonical? When they map canonical inputs to canonical outputs. So that's what we say here, is that this term with a function type maps canonical inputs to canonical outputs. And if we have all this data, then we can say that we have a canonical term of this form, which is now a type for a code for a function type. But this whole thing, it has to be inductive recursive itself, because we need to refer to what it means to have a canonical term with EL type. So that's what we have to compute by the recursive component of this definition. So it gets a little bit more complicated, but the basic idea, like going from natural numbers to this, and then going from an inductive recursive type to this, it's essentially the same idea of a logical predicate interpretation. But then the complication is, but code is a single inductive recursive type, but we want to show canonicity for all inductive recursive types. So we need to specify and assume all inductive recursive types in the object tree, and then repeat this construction generically for all inductive recursive type descriptions. And just shortly, I'm not going to go into the details, but just to kind of give a taste of what is the general specification for inductive recursive types. So I think that this is quite brilliant, and it's very concise, but it's a bit kind of brain twisting. But basically, I'm just reusing the same definition that was given by DBA and Zetzer for the signatures for inductive recursive types. And an interesting thing about this is that the description of inductive recursive types is itself just an inductive type. And the inductive type is some kind of fancy telescope. And so let's just try to go through one example. So once again, exactly the same code example that we had before. And maybe it's going to be slightly clearer if I just explain what this signature here means. So the first thing that we have to do is to specify how many constructors do we want to have in the definition. So you can see here that we have two different constructors for this inductive recursive type. So we have to pick bool as like the number of constructors, essentially a tag that we can dispatch on. And in one case, we want to specify the natural number code, and in the other branch, we want to specify the code for dependent functions. And in the case of the natural numbers, here, we just specify that this constructor is being interpreted as the set of natural numbers, and that's what we have here. So here we have that the EL of encode, not code, is not. And then in the other case, it's a bit more complicated, but basically we have to introduce some inductive fields, and in the end, we have to specify that this thing itself is being interpreted by the recursive function as a dependent function type. And then for each signature, We also need to assume that we have a type formation rule, so that for each signature you actually get a type, which is the inductive recursive type. And then we also get term formation, which is just constructors. And then we have elimination with some beta rules as well, which I omit here. Okay. And now how to do the general canonicity proof. So it's a bit technical. So here I only try to give some computational intuition because the proof itself is actually constructive. So you can just view it as an evaluation algorithm. More concretely, so this logical predicate interpretation, you can think about it as type-directed closed evaluation. And then the canonicity witnesses, so essentially like the values which witness these canonicity predicates, you can think about them as runtime values. And I think this is a good intuition, but of course it's still technical, even if we try to use this intuition. So, for example, how would we try to evaluate a type former? So this IRS now is just a type former. It's an inductive recursive type constructor for some S, and this S is a signature now, so this fancy kind of telescope that we have here. Well, what we do is that first we have to evaluate the signature itself, because the signature itself is just an inductive type, which is internally present in the object language. So first you evaluate the signature, and then we do induction on the value of the signature to compute the meta-theoretic canonicity predicate, which is an indexed inductive recursive signature in the meta-theory. And then we take the meta-theoretic indexed inductive recursive type to get this canonicity predicate, which is going to be the actual result of evaluation here, because here we are just evaluating a type former. And then for the term constructors and the inductive recursive elimination principles, we have to use the corresponding meta-level index inductive recursive constructors and eliminators. And this is not too bad, but basically everything has to be done generically over signatures and by induction over signatures. And there are like a bunch of equivalences that we have to kind of trip through to make this construction work. Okay. And what about index induction recursion? Because it's in the title. So the title says something about canonicity for index induction recursion. But this is relatively easy because we can just construct indexed inductive recursive types from inductive recursive types. And the idea is well known. It's well known is kind of the forwarding translation when you convert indices to parameters and propositional identities. So this is fairly straightforward. Maybe slightly interesting is that because in this construction we work in plain Martin-Löf type theory, we don't have uniqueness of identity proofs. We have to do a little bit of homotopy type theory to actually make it work. So we need to rely on properties of equivalences and actually real equivalences and not just isomorphisms of types. Okay, and this one I can probably skip. And okay, so what do we have, like overall? So first we have that indexed inductive recursive types can be constructed just from inductive recursive types and basic type formers. And then we have that for Martin-Löf type theory with countable universes and induction recursion in every universe, we can prove this system to be canonical by extensional type theory with countable universes with induction recursion, plus 2 more universes on the top, which is, of course, there has to be something more because otherwise we run into kind of Gödel issues. So you need to have more universes in the meta theory than in the object theory. And then this system is proven to be consistent by DBA and Zetzer. So this is basically just an adjustment of all the work by DBA and Zetzer. And we kind of just convert IR universes with IR to Malo cardinals, and then these 2 universes to inaccessible cardinals. Okay, what about future work? What about normalization? Because that's what we need to have kind of implementations of proof systems. So we need normalization in order to get conversion checking. But here, it's a bit of a complication. So if you want to work in a kind of a nice algebraic or even synthetic setting for the normalization proof, we would like to work internally to presheaves. So we need the inductive recursive predicates inside presheaves, but this doesn't exist in the literature. So first we have to give a model of inductive recursive types and presheaves, and this is already roughly as much work as doing this canonicity proof. And then from that, we can proceed and actually try to do the normalization proof. What about canonicity for other kinds of fancy inductive types? So I think that the technique here is applicable. Some things seem easier, and then some things seem harder. And then we can also try to generalize the proof itself. We can try to view it as some kind of parametricity translation, or we can try to view it as even more generally as some kind of model construction. And okay, thank you.
Thanks for the talk. I fear because of the technical difficulties we have time for one very quick question, if there is any, while the next speaker already sets up. Any questions? Can you reuse some of the canonicity results that you proved on the way to normalization? Are there connections between the formalization that you did and what you need to do for a normalization?
So the question is what I would need to do. Okay, so can I reuse?
Whether you can reuse parts of your formalization.
I mean, yes, I can reuse many of the patterns, but this is a general curse in type theory, is that even you can reuse ideas and patterns, you cannot actually reuse exactly the things. So going from canonicity to normalization, we have to go, we have to add the notion of neutral values everywhere in the semantics, and that's kind of the main thing which just spices everything relative to the canonicity proof.
Okay, I think in the interest of time, let's thank the speaker again. Is it still on? Yeah. Next talk will be about co-recursion. In particular, it will be about a framework for defining co-recursive functions in ROC. The paper is by Jae-woo Kim, Jeon-woo Nam, and Chung-kil Hua. And the talk will be given by Jae-woo. Please.
Present a COCO for co-recursion with compositional heterogeneous productivity, which is joint work with Yeon-woo Nam and Professor Chung-kil Hua. I have structured this talk into two main parts. First, I'll explain how co-recursive definitions work and the challenges they introduce. Then, I'll present our key approach to resolving these challenges. We will start by introducing co-inductive types in comparison to inductive types. On the left, we have a standard binary tree, which is finite. This is a typical example of an inductive type. On the right, however, we have an infinite binary tree. This is the key difference. While inductive types are for finite data, elements of co-inductive types can be possibly infinite. This allows us to use them for modeling infinite structures and behaviors. In this talk, I'll focus on the stream, which is the canonical example of a co-inductive type. In ROC, we define it using the co-inductive keyword to mathematically represent infinite sequences of integers. This definition gives us the constructor S-cons of type into stream, denoted here by the double colon. For this type, we also have the natural destructors as head of type stream to int and as tail of type stream to stream. To construct elements of a co-inductive type, we use co-recursive definitions. For example, let's look at zeros, a stream consisting of infinitely many zeros. Its first element is 0, and the remaining tail is, once again, just zeros. Because of this self-similarity, we can define it cyclically. We view this stream as the fixed point of the generating function, lambda self 0 ascons self. The cofix operator, colored red, returns the unique fixed point of this generating function, provided that a unique solution exists. Let's expand this definition step by step. If we unfold zeros here and substitute it with 0 ascon zeros, we get this. And if we unfold zeros here again, we get this. And it produces element 0. The stream is uniquely determined, so we say it is well-defined. However, not every cyclic definition is well-defined. Consider ill defined as the fixed point of lambda self self. Expanding this definition simply yields ill again and nothing more. Since it fails to produce elements, the stream is not uniquely determined. Therefore, we say this is ill-defined. However, there is a limitation in Rock's handling of co-recursive definition. Consider growing, defined as the fixed point of lambda self 0 ascons as map as self. Here, as map as simply increments every element of a stream by 1, as in the example on the right. Let's expand this definition step by step. If we unfold growing here, substitute it with 0 ascons as map as growing, and simplify it a bit, and unfold growing here again, we see it produces elements without issue. Conceptually, this should be well-defined. However, Rock rejects this definition since the Rock checker does not know that SMAP-S is safe here, that is, it preserves productiveness. Rock is being conservative. After all, if SMAP were an arbitrary function, the definition would not be guaranteed to be well-defined. Now, let's look at existing solutions to this problem. First, there is the contraction method. Here, the user can manually prove the contractivity property of a generating function to guarantee that its fixed point is well-defined. However, a limitation of this approach is that it is not compositional. That is, we cannot decompose the property into components and derive the overall property from them. Also, there is a MICO, which achieves a degree of compositionality by introducing the friend concept. In a sense, functions are registered as friends based on their syntax if they produce n elements by consuming n elements. Then, the Amico library can automatically validate co-recursive definitions composed of these friend functions when it is guarded by an additional constructor. Let's look at our example growing again. Here, SMAP-S produces n elements by consuming n elements. In the example on the right, if the input has 2 elements determined, the output of SMAP-S also has 2 elements determined. Therefore, it can be registered as a friend, and growing can be accepted. However, the compositionality offered by MICO has its limitations. Consider Fib, the Fibonacci string, defined as the fixed point of lambda self, 0 ascons, 1 ascons, addition of self and S-tail self. Here, the plus sign notation is for the element-wise addition of the streams. Ideally, we want to decompose the function into components such as ascons, element-wise addition, and S-tail, and prove it is well-defined simply by composing their properties. Nevertheless, S-tail is not a friend. This is because it consumes 1 more element than it produces. Therefore, we cannot verify Fib in this form using the friend concept alone. Our work extends this compositionality further using CHP, compositional heterogeneous productivity, by assigning quantitative productivity values to component functions. This enables greater decomposability and widely applicable automation. COCO is our implementation that uses this theory to automate this process. This brings us to part 2. Now I will explain the key ideas behind CHP and COCO. So, how do we introduce quantitative productivity? Let's start with a naive integer-based approach. First, we assign integer productivity to component functions. For example, sconst is assigned +1 since it produces n plus elements by consuming n elements. In the example on the right, we see that providing 2 input elements determines 3 output elements. Similarly, stail is assigned -1 since it produces n elements by consuming n plus 1 elements. In the example on the right, we see that providing 3 input elements determines 2 output elements. And smap S is assigned 0 since it produces n elements by consuming n elements. In the example on the right, we see that providing 2 input elements determines 2 output elements, the same amount. Next, we sum these values to derive the total productivity of the generating function. If the result is positive, that is greater than or equal to +1, then the fixed point is well defined. Let's look at examples. For zeros, the generating function uses sconst once, so its productivity is +1, confirming that it is well defined. Conversely, for il, the productivity of the generating function is 0 because there are no components to consider in the counting. So il is ill-defined. For growing, there is one sconst plus 1 and one smap s, 0, so the total productivity is +1 plus 0 equals to +1, identifying it as well-defined. However, this naive mechanism falls short in some cases. Consider S1 defined as the fixed point of lambda self, asset self sconst, one sconst, stail self. There are 2 sconsts and 1 stail, so if we calculate the productivity using simple sum, it evaluates to +1 plus 1 minus 1 equals to +1. Yet, if we expand the definition, unfold S1 here, and simplify it, we hit a deadlock. We get that the head of S1 is asset S1, and nothing further happens. It does not produce the first element, so it is actually ill-defined. Intuitively, asset consumes data in some way, so it needs to be taken into account in productivity counting. But there is a problem. Asset returns an integer, not a string. So the meaning of productivity for asset is unclear. There are no elements to produce or consume for integers. Still, to proceed, an ad hoc fix for this is to assign -1 to asset, reducing the total productivity to -1 plus 1 plus 1 minus 1 equals to 0. Now it correctly reflects that S1 is ill-defined. But this fix still has a problem. Let's apply this ad hoc assumption to another example. S2, the fixed point of lambda self, 0 sconst, asset self sconst, stail self. There are 2 sconsts, 1 asset and 1 stail, so the productivity sums to +1 minus 1 plus 1 minus 1 equals to 0. This suggests that S2 is ill-defined. Nonetheless, when we expand the definition, unfold S2 and substitute it with 0 sconst asset S2, sconst stail S2, and simplify it a bit, it successfully produces a stream of zeros. So this is actually well-defined. This shows that we cannot simply assign productivity -1 to S head. Then, what is the correct productivity for S head? CHP solves this problem by generalizing the notion of integer productivity to handle heterogeneous type. Let's look at how this works in detail. In CHP theory, to handle various domain and codomain types, we assign a specific level set and a corresponding equality up to relation to each type. For stream, the natural level set is net. Two streams are equal up to n if the first n elements coincide. For example, any two streams x and y are equal up to 0. Also, 42 as cons x and 42 as cons y share the first element 42, so they are equal up to 1. For int, we use a different level set, bool. Two integers are equal up to true if they are identical, and any two integers are equal up to false. For example, 42 and 42 are equal up to true, but 42 and 37 are only equal up to false. The level set of int times stream follows naturally from this. It is the product of the two level sets. Two pairs are equal up to a level L1, L2 if the first elements are equal up to L1 and the second elements are equal up to L2. Therefore, 42 and 0 as cons x and 42 and 0 as cons y are equal up to true and 1. Crucially, COCO selects the level set for these types and other types automatically. Now, let's look at the formal definition of productivity. Consider a function f from type C to D. The productivity P is defined as a relation on the level set of these types, level of C and level of D. We say that f is P productive, or f has productivity P, if it satisfies the following condition. For any output level L out, if two inputs C1 and C2 are equal up to all input levels L in related to L out by P, then the outputs f of C1 and f of C2 are equal up to L out. With this definition established, let's apply it to our standard constructor and destructors. For ftail to produce n elements, we need n plus 1 elements from the input, so the productivity relation requires n in to be equal to n out plus 1. We also include the condition n out is greater than 0 in the productivity, since no input elements are needed to determine 0 elements in the output. In the example on the right, we see that when two input streams are equal up to 2, two output streams are equal up to 1, which matches with the productivity. For ascons to produce an element, we need a valid integer for the head and a tail of length n minus 1, which is why there are two conditions, b in equals true and n in plus 1 equals n out. In the example on the right, we see that when two integers are equal up to true and two streams are equal up to 1 in the input, two output streams are equal up to 2. This matches with the productivity. For set to produce an integer, we need at least one element, so the condition has n in equal to 1. We also include the condition b out is true in the productivity, since the equality up to false trivially holds. In the example on the right, we see that when two input streams are equal up to 1, the output integer is equal up to true. COCO generates these productivities automatically. Furthermore, these productivities are compositional. We establish this via composition lemmas for standard combinators, such as the constant function, sequential composition, and pairing combinators shown here. Each lemma shows exactly how to compose the productivities of the component functions. For the constant function, the corresponding productivity is just the empty relation, or false. For sequential composition, it corresponds to relation composition, and for the pairing, it corresponds to a form of disjunction. Similar lemmas exist for other standard combinators. Currently, to use these compositional lemmas in COCO, the function must be provided in combinator form using the combinator shown on the previous slide. Note that if we unfold these combinators, we recover the original definitions. Thus, they are definitionally equal in this case. Automating this translation to combinator form is a topic for future work. Now, let's see how productivities are composed in action using the example S2. We will show the productivities of intermediate functions step by step. Note that each function and its corresponding productivity are color-coded to match. We start by pairing shead and stail using the pair lemma to obtain the intermediate productivity. The disjunction that was in the lemma appears here. Next, we compose this result with ascons using the sequential composition lemma. Now, relation composition is used. We see this in the form of the existential quantifier exist N1, B1, and the conjunction. After that, we pair this result with const 0, using the constant function lemma and the pair lemma. We see another disjunction, including the occurrence of false. Finally, we compose this result with the outer ascons using the sequential composition lemma again. We see another relation composition. This gives us the total productivity of the generating function of S2. Finally, we compare our composed productivity against a reference productivity, one that ensures progress shown here in pink. This loosely corresponds to the +1 requirement in our previous naive approach. If the derived productivity is included in this reference productivity, the fixed point is guaranteed to be well-defined. The inclusion condition is expressed here by the right arrows implications. For S2, this condition is satisfied, so the fixed point is well-defined. COCO generally automates these checks using a specialized tactic, primarily based on the NIA solver. Let's do this one more time with S1. Here is the derived productivity from the composition lemmas, and here is the condition. For S1, this is not satisfied. We can find a counterexample when N0 equals 1 and N3 equals 1. This matches the fact that the fixed point is ill-defined. In our paper, we provide the full details on how to assign productivity to functions of arbitrary types. For example, even a function from the sum of stream and binary tree to the product of stream and integer. Furthermore, we present composition lemmas for a wider range of combinators, including function product, copair, and coproduct. The one other important concept I haven't mentioned yet is second-order productivity. The question might arise, how does COCO know that S map S is zero productive? While it is possible to prove this manually, our second-order productivity is the key to doing it automatically. We won't go into detail about the definition of second-order productivity here, but it is compositional, just like the first-order productivity. From this, we can derive the productivities of more complex and interesting examples using our theory, including ones for mutual co-recursion. These are in the paper and in the artifact. In conclusion, CHP enables the compositional calculation of productivity for heterogeneous component functions. Complementing this theory, Cocoa is our rock library implementation that provides high automation for this process. We have several directions for future work. Here we highlight some of them. First, compared to tools like Amico, Cocoa currently requires more boilerplate code, and we aim to improve our engineering of low-level automation to increase usability for the general user. Also, while mixed recursion co-recursion inherently requires a kind of termination proof, there is room for improvement in the automation support for this in Cocoa. Additionally, we plan to port our library to Lean, another well-known proof assistant. Thank you for listening.
Thank you. We have time for maybe 1 or 2 quick questions.
Thanks for the talk. I think this work is quite kind of related or comparable to guarded type theory, which uses step indexing or crypt key semantics to deal with like semantic notion of productivity, which is actually contractivity in their theory. So I think the main difference is the index is like usually natural number or globally fixed in their work, but in your work it's local. But in guarded type theory, it has a kind of advantage that like it can handle like higher order data types, like function can be under the later modality like that. So how do you think like guarded type theory and your work can be combined?
Thank you for the question. I think our work and the guarded type theory took different approaches. We do not have to change the types in our theory, annotated with some numbers. And as far as I know, guarded type theory requires some numbers as in size type or some modalities. And we do not need that, and this information is included in the productivity. And also about the function, our theory and Cocoa can also deal with functions. A function is just another type combinators that can be handled by Cocoa. And also there is the theory of second order productivity, which also gives the productivity of the fixed point of the generating function, not just the existence of the generating function's fixed point. So does this answer your question?
I wanted to ask about like non-monotone data types, like because function is covariant, contravariant in the argument. But maybe we can discuss offline. So thank you.
Okay, thank you.
I fear we have to move on. Let's thank the speaker again. Please do ask the questions offline if you have. The final talk of the session will tell us how to do pen and paper style equational reasoning in an interactive theorem prover using equality saturation. The talk will be given by Markus Rossel, and there are many co-authors. I will read them out. Rudi Schneider, Thomas Köhler, Michael Stoiber, and Andres Goerns.
Right. Okay, thanks. I can tell it's the sleepy time of day, so I hope to get you through the next 20 minutes until the coffee break with an easy topic. It's more applied, less theoretical. I'm not going to read the title again, that's going to take a while. So I'm going to assume that everybody here knows what an interactive theorem prover is, but for those who don't, the 5-second explanation is that it's a software system in which you can state proofs and have the system check whether your proof is correct. So as an example, here I have a proof written in the language Lean, and it looks kind of like code, so it should be somewhat familiar feeling, and I hope you can all see what we're proving on this slide, right? Because I certainly can't really tell what's going on here. And that's because the actual intuitive reasoning steps that you would do on paper are just clouded in a sea of justifications, which are necessary for the interactive theorem prover to accept your proof. So if we remove those for a second, then we can kind of see what's going on, right? We're just proving a chain of equalities here, which are actually part of the proof of the binomial theorem. And this looks much closer to what we would maybe write on pen and paper. So the goal of our work is to join these worlds more closely, to allow you to write what you would write on pen and paper almost exactly the same way in an interactive theorem prover. Okay, now the way we go about this is by connecting two tools. On the one hand, there's the interactive theorem prover, as I mentioned, Lean. And on the other side, there's a tool for automated term rewriting, or more specifically, equality saturation, called Egg. And so the way we connect these two tools is by a proof tactic, which takes in a given proof goal, a user-provided set of theorems, translates these into the world of Egg, which is using an egraph and rewriting rules. Then we run the aforementioned procedure called equality saturation. And if the engine is able to prove our proof goal, then it can provide an explanation for us, which is a certain kind of proof witness, which we use to reconstruct a proof in Lean. So in a very trivial way, our approach is sound because we're producing a proof term in the end, which is checked by the interactive theorem prover. So if we produce something that is incorrect, it's just not going to pass. Now, from a more in-depth perspective, what we're doing is absolutely not sound. So in the world of Egg and egraphs, we are performing steps and running rewrite rules which aren't necessarily sound, so things can go wrong. Now, one important source of such unsoundness is the translation from theorems to rewriting rules shown at the top, because theorems come with a lot of, let's say, semantics, and rewrite rules are just syntactic transformations. So that's what I want to focus on in this talk. But before we get to that, I briefly want to explain a bit more what egraphs and equality saturation are, because maybe not everybody knows about them. So a very brief explanation of what an egraph is that it's a data structure for representing both terms, many terms, and an equivalence relation over those terms. Now, a very simple example of this would be to start with a concrete term like the one shown here, which we might use in our binomial coefficient proof. And so this is just the term n plus r minus 1 plus 1, represented as an AST. Now, if we want to turn this into an egraph, the first step is to combine shared subterms. So that's pretty simple. The second step is to introduce this notion of equivalence classes, which we're going to write as dotted boxes. So you can see here in this egraph, a priori, every term and subterm lives in its own equivalence class, because a priori, we don't know that any two terms are equivalent. But now I'm going to start shuffling things around a bit. This is still the same egraph, because in a moment, we're going to perform an operation which is very common on egraphs, which is rewriting. So for that, we provide a rewrite rule, which in this case states that any term of the form x minus 1 plus 1 can be rewritten to the equivalent term just x, where the leading question mark indicates that this is a pattern variable, so it can be matched against any term in the egraph. Now, if we actually run this rewrite rule or apply it to the egraph, you can see what happens. Namely, we've merged the equivalence classes of the term n plus r and n plus r minus 1 plus 1. So you can see rewriting in an egraph doesn't actually destroy anything. It doesn't lose information. It only adds more information to the egraph, which is why this is a very useful data structure and procedure for using rewrite rules which would otherwise not be useful in something like a greedy simplifier. Okay, so this is an egraph, and the final step, which is actually important, is that we are now going to only consider terms up to equivalence of children. So these boxes are now called e-nodes, so they don't represent single terms anymore, they represent families of terms. For example, the minus node now points to the equivalence class of n plus r. Okay, so that's an egraph, and equality saturation is now simply the procedure of taking an egraph and a given set of rewrite rules, applying the rewrite rules iteratively until we either reach a fixed point, which almost never happens, or until some user-defined timeout is reached. Okay, so equality saturation, for our purposes, is kind of a solved problem because there exists this egraph library, Egg. So the part that we need to focus on in our approach is actually how to get from Lean to Egg and back. And that's where encoding theorems as rewrite rules comes in. Now, to first demonstrate what the differences are between theorems and rewrite rules and how we can run into difficulties, I want to show two simple examples. The first one is going to work out well. So this theorem that we could state in this way in Lean just states that addition of natural numbers is commutative. And for this theorem, there's a very natural interpretation as a rewriting rule. Namely, we just consider the left and the right-hand side of the equality as the left and the right-hand side of the rewriting rule. So this rewriting rule would allow us to merge the e-classes of any terms a plus b with b plus a. Now, there is some slight loss of semantics here, because in the theorem, for example, we have a typing annotation. We say that a and b have to be natural numbers. In the rewrite rule, we lose that because it's just syntactic. But for our purposes, that's sufficient, because as mentioned, we can do some unsound stuff in the e-graph and not worry about that as our proofs are checked at the end. Now, an example of a rewrite rule that actually breaks comes from the following theorem, which is more representative of a general class of theorems, namely equations with conditions on them. So here, the theorem states that n divided by n is equal to 1 under the condition that n is non-zero. And if we, again, apply the naive translation to a rewrite rule, we get the following. Now, I hope you can see why this is a bigger problem, because this rewrite rule could easily apply in the e-graph to a term which is actually equal to 0. And the reason this is actually a problem, namely ignoring the conditions is a problem, is because recall in our approach, we actually have to do proof reconstruction at the end. So if we apply a rewrite rule which supposedly corresponds to a theorem, and then we get a proof in this way, then we will not be able to apply the theorem at the end if the rewrite rule is too unsound. So what we really need from our translation of theorems to rewrite rules is that the applicability of the theorem should to a certain degree follow from the applicability of the rewrite rule during equality saturation. Or stated more in other words, we have a requirement on which theorems we can translate to rewrite rules, namely the theorem's quantified variables should all be determined by the rewrite rule when it is applied during equality saturation. Now, from this requirement in our paper, we derive a given set of rules on which theorems we can effectively translate to rewrite rules. But I don't want to go into those as they're a bit technical. I instead want to show one example of how we go from a theorem to a rewrite rule and solve the problem of translating a theorem like the one shown here. So the one example we're going to look at is the following. It's a slight generalization of the theorem we just saw before. Namely, we generalize it from natural numbers to any field. So for any field f and any element of that field, if n is non-zero, then dividing the number by itself is equal to 1. So recall that the applicability of the rewrite rule, which should correspond to this theorem, is constrained by the fact that we want all quantified variables to be reconstructible after the fact. So I'm just going to list the quantified variables here explicitly, and I'm also going to change the statement of the theorem to match that. And now our goal is to construct a rewrite rule which somehow allows us to determine each one of these quantified variables. So let's start with the naive translation again. In that case, you can see that if we apply this rewrite rule during equality saturation, we obviously know what n is, and we also happen to know what f is because this division operator is just syntactic sugar for a more underlying application which also involves the type. So the naive translation allows us to determine n and f. So next, we want to think about how to also obtain a proof that n is non-equal 0 and make that part of the rewrite rule. So the way we're going to go about this is to change the left-hand side, so the pattern of the rewrite rule, to include a term which can only be matched when the condition holds. So we're going to write something like this. So on the left-hand side, we now have what is called a multi-pattern, so a set of patterns which need to be matched in order for the rewrite rule to apply. And one of those terms is now fact of n is non-zero. And again, this term should only exist and be matchable if n is actually non-zero. And so to construct such a term, we use the following construction. Namely, it relies on the basic observation that any proposition holds if and only if it is equal to the proposition true, which is useful in the context of an e-graph, because in an e-graph, you can talk about equality of terms easily by them being in the same equivalence class. Okay, so P holds if and only if it lives in the same equivalence class as true, and the way we now construct a term which only exists when this is the fact is as follows. We introduce a new special e-node called fact, which lives in its own e-class, and its only purpose is to point to the e-class of true. And what this means is that the term fact P, for any proposition P, exists only if P is in the same e-class as true, which recall holds if and only if P is true. So fact P exists only if our condition holds. So that's why this multi-pattern construction works. The rewrite is only going to apply when fact of n is non-zero exists. And in that way, we know if this rewrite was applied, then during proof reconstruction, we can query the e-graph and ask, hey, how did you figure out that n is equal to non-zero is actually in the same e-class as true, which is going to yield us a proof of h. So we have that covered now too in this setting. Now the final quantified variable is a bit different from the others in the sense that it's a type class instance. And type class instance or type class synthesis isn't really amenable to be encoded in an e-graph. It's a much different procedure. So in this case, we want to ensure that f has a field instance by actually calling Lean's synthesis procedure. And to do that, we have to take a bit more of a, let's say, implementational view on what a rewrite rule is, which is luckily also a view that was given in the original equality saturation paper and is supported by the library. And that view on rewrite rules is the following, namely, where right now a rewrite rule consists of two patterns, we can think of it more computationally as consisting of a left-hand side, which we'll call the searcher, which is some procedure used to derive a set of substitutions for the given pattern variables. So providing a pattern is a very natural way of specifying what that procedure should be, but really it could be an arbitrary computation. Now the same goes for the right-hand side of the rewrite rule. After the searcher produces a set of substitutions, the applier can simply modify the e-graph in any way it wants based on that substitution. Now again, providing a pattern is a very natural interpretation. So what we are going to do is we're going to change the applier such that it runs type class synthesis and only proceeds if that was actually successful. So going back to our example, we're going to change the right-hand side to a bit of pseudocode here, which states that if the left-hand side of the rewrite rule matched, then run the right-hand side, which checks if in Lean field of f can be synthesized. If that proceeds, merge the e-classes of n divided by n and 1. If it doesn't proceed, simply abort the rewrite, don't apply it. And again, using this approach, we now know if this rewrite rule goes through, then during proof reconstruction, we can synthesize an instance of field f, which we can then use to instantiate the theorem above. So in that way, this variable is also covered. Okay, and since we have now covered all quantified variables, we know that when the given rewrite rule applies, during proof reconstruction, we should be able to actually apply the theorem above, as we can find an assignment for each quantified variable. I write should be applicable here, because recall, the procedure that we run in the e-graph isn't necessarily sound. We can do some unsound things. So since we can't give theoretical guarantees, the question becomes, can we give practical examples where our procedure does actually work well? And we have 4 of those in the paper. I just want to show you 2. The first one is the example we saw in the beginning of the binomial theorem. Recall that originally we had to provide many justifications for why each of these proof steps actually holds. But using our tactic, we can actually rewrite this as follows, which is using our tactic called egg, we can provide all of the equational reasoning steps without any further justification and just move all those justifications to the top, where this plus cast indicates a set of lemmas for casting between natural numbers and reals, and the plus real provides a set of lemmas for real arithmetic, and the gamma stuff are just 2 additional lemmas we need in this case. And you can see here that this is pretty much what we would have written on pen and paper. And here precisely we're using an approach actually called guided equality saturation, which splits up one long run of equality saturation into multiple sub-steps, which in this case simply correspond to the equational reasoning steps that we provide explicitly. So that's the first example. The second example I want to show you comes from the domain of functional array programming. So there's this paper shown here in figure 6, which introduces a bunch of rewriting rules for the purpose of optimization. And in the paper, they also prove correctness of these rewrite rules. In their case, they formalized their proofs in Agda. And so in our use case, we also reproduced this using our tactic in Lean. And what we found is that for all of the rules that they show, first of all, these rules involve length index lists, so dependent types, as shown in the first example. And in the second example, we also have to handle binders. And in all of the examples that they formalized, we noted that we could solve them by just performing induction and case splitting up front, and on all sub-goals produced by this, running our egg tactic. And we're able to solve all of the theorems just in this way. Okay, now before I finish, I also want to mention 2 items of related work. One is called Coquetier, written by Thomas, who might be in the room or at least is at this conference. It's a very similar tool, but written for the ROC theorem prover, which also translates theorems into rewrite rules in egg, but more at a vernacular level. In our approach, we go more to the underlying type theory level of Lean. And they are also able to prove other kinds of goals like existentials. And the second very closely related item of related work is the grind tactic, which was more recently released by the Lean developers. And this tactic also is based on eGraphs, but it also integrates more SMT-based techniques like satellite solvers. And we have a brief comparison to their tactic in our paper. We were able to solve some goals, which they weren't, but it is currently still unclear when our tactic proceeds and theirs doesn't, as there isn't that much existing documentation for their approach. Okay, and with that, this is a QR code to our implementation. Definitely check it out if you're interested, or check out the grind or the Coquetier tactic. And with that, I'm open for questions.
Thanks for the talk. I see many questions.
Thank you. This is very nice. About the example on slide 52, where you showed just the equational reasoning steps, here, if you wanted to skip all of the steps and go straight from the beginning to the end, would it still work?
No. So this is a case where, so this approach of guided equality saturation was derived precisely from this need of handling larger examples, because equality saturation has a tendency to just explode the eGraph. So yeah, in this case, we might be able to skip some steps, but I'm sure I tried it without any steps and that didn't proceed. It would just blow up the eGraph too much. Yeah. But I think it's a very nice coincidence that the theorem proving use case is very naturally lends itself to this guided equality saturation approach, because it closely resembles what you might do on pen and paper. You just add another equational step.
Yeah. Hi. Nice talk, thank you. So I'm curious what you call an explanation. In the beginning, I'm assuming that sometimes the proof assistant will reject correct explanations. Is that correct?
The proof assistants will correct,
so if I have a correct explanation, right, it might be the case that the proof assistant would reject that even though it's correct.
I think, well, if that is the case, that would just be a bug in our proof reconstruction. So as long...
Maybe not necessarily a bug, but is it possible for the user in that case to like somehow interact with the explanation in order to get the proof assistant to accept it?
No, so the only way you could currently interact with that in our implementation is you can look at the explanation, but that's not going to be a lot of fun. But yeah, we don't currently have an approach to massage the explanation into something that the theorem prover could accept. That's actually a good point. Yeah, we should support something to, let's say, to fix up the broken parts in an interactive way. Yep.
Thank you.
Hi. Here.
Yeah. Hey.
Thanks for the talk. It was very nice. I was wondering, so the way I understand things for now is basically when you're trying to prove a precondition, you're basically proving this inside of egg by doing basically only equality reasoning. Would it be possible instead to call in the automation of Lean itself the way you do for type classes? And also one thing that or like somehow use because I feel that this is quite limited, that the only hypotheses that you can discharge are those that are provable purely by equational means. I have the feeling it will not go very far. So have you thought about this?
Yeah, so first of all, yeah, we also considered adding other decision procedures to discharge equalities. That's, for example, something that grind would do very well. Yeah. So we take a different approach. We take more of the rewrite tactic approach, which is we can surface proof obligations interactively as we can surface non-proven conditions as new proof obligations to the user after the fact, which is, for example, used in the example shown here. I just didn't show the rest of it. And this works well in some examples, but not in others. So this is, I think, also, for example, the reason why the lean simplifier doesn't do this, at least yet, is because once you allow arbitrary conditions to be kind of postponed, things can go wrong. But in this example, it, for example, produced precisely the preconditions that we also proved by hand. Yeah, so we have a mode for this, but it's kind of a gamble whether it works well or not. Yeah.
Okay, I think it's okay. One last question.
Right. Thank you for the talk. I was impressed by your facts. This idea seems quite clever. Could you compare it? So I think you can do conditional rewrite rules where you can depend on the analysis data, the analysis data to do conditional rewrites. And this example where you have division by zero is, a standard example in which if you try and use the analysis data to decide whether you can or not apply the rule, you might just get into trouble because at some point you will look at n, the analysis data is not zero, you apply the rewrite rule, and then at a later point you'd figure out that n is in fact zero, and now it's all gone wrong. So would you mind just comparing a little bit how you can not have this issue with fact? Maybe I think I didn't get it fully, but it seems quite clever.
Yeah. So here, in order for this rewrite rule to go through, you in a sense need to proactively already have proven that n is non-zero, right? So in this case, if you haven't yet proven that n is not equal zero, the rewrite rule won't go through. So in that sense, it's kind of the other way compared to the analysis approach, right? Does that answer your question? Okay. It's either given or derived some way. So yeah, as a user, you can just input facts into the egraph at the beginning, but also we rewrite on those facts, so we can also automatically derive new facts in the egraph. Yeah. But you're touching on an important point, which is if you don't seed the egraph well with good facts, then you might just not discover something like n being non-equal to zero. Yeah.
I think it's time for coffee, so let's thank this speaker and all speakers of the session.
The feedback will come here, and as long as you see it here, they will see it behind you.
Thank you.
All right, and our next speaker, Nicholas, is going to tell us about Salvation by the Compiler, which in this building seems like an appropriate title.
Thank you. So I'm happy to tell you how compilers can bring security guarantees to unsafe languages and present how we can verify that. My name is Niklas Mück, and this is joint work with Einar Lind-George, Derek Dreyer, Deepak Garg, and Michael Samler. So let me start with an example. Here we have a program that allocates two local variables, x and private. It then passes a pointer to x to an I/O library in order to read an input. And afterwards it asserts that the private variable did not change. The interesting thing about this program is that this library is untrusted. Imagine that it is some library that a programmer of this program has taken from the internet without inspecting the source code. So we know nothing about this I/O read library, and it could even be maliciously crafted. And we are at POPL, so we would like to verify this program. Concretely, we want to verify that this program has no failing asserts. But what does this even mean? I mean, there's this library call we know nothing about. So the best thing we can do is to quantify over all possible implementations of I/O read, and then study our program when linked together with such an arbitrary implementation. This property is a well-known security criteria called robust safety, and will be the attacker model for the rest of this talk. So we'd like to verify the robust safety of this program, but does this property even hold? This depends on the programming language the program is written in. And I have bad news for you. This program is written in C. And the program is not robustly safe in C. To see why, let's consider an example implementation of I/O read that attacks the program. It takes the pointer to x, then subtracts 1 from it, and tries to store 0 to the address aligned next to x. And in fact, if we compile this program with GCC, the assert fails. The reason for that is that this out-of-bounds access here is undefined behavior, which means that the compiler is allowed to do anything. GCC exploits this by aligning the two variables x and private next to each other in memory without any protection mechanism. So as soon as an attacker is able to trigger undefined behavior, there are no guarantees according to the C standard, so this program is not robustly safe in C. Does this mean we are out of hope? Well, I said a compiler can do anything. This also means that a compiler can choose to make the program robustly safe. Compilers, as such compilers that introduce security mechanisms, are called hardening compilers. So even though a program is not robustly safe in C, the compiler can choose to harden the program such that the compiled program is robustly safe. Let's see what this means to our example program from the beginning. We want to build a compiler that can harden the program such that the compiled program is robustly safe. At first, the bottom line there might look like the robust safety property from the beginning that we said does not hold, but note that we have the compiled program there that is not linked with an arbitrary C library, but with an arbitrary low-level context. And I would say this is the actual property we care about, because in the end we never execute C directly, but we always execute a compiled program. So does this sound good? You probably wonder how a compiler can achieve something like this. And in fact, there are many ways. But we focus on hardening compilation via compilation to capability machines. Capability machines are a special kind of CPUs that perform dynamic security checks at runtime. So let me explain the key idea. The problem with standard assembly is that a pointer is just an integer, the address, from which the aligned address can be computed from and then accessed. On a capability machine, however, a pointer is a capability.
and such a capability is needed in order to access memory. A capability is such a tuple that does not only consist of the current address, which we have in orange, but also has a permission tied to it, for example, read-write permission, and more importantly, it also has bounds. And, well, the hardware then checks that you have the right permission and that you only access memory within the bounds. So let's consider the attack from before again, that adds -1 to an address and then tries to store 0 to it. If we now give this attacker only a capability with bounds for x, then this attack is detected by the capability machine as illegal and prevented at runtime. And the compiler can make use out of this. If a compiler compiles local variables to capabilities with disjoint bounds, it can rely on the capability safety of the hardware. So now you hopefully have a rough idea of how one can build such a hardening compiler. The big question we studied in this project is how to verify such a hardening compiler. And in fact, we are the first one to study the verification of these kind of hardening compilers for robust safety. And that's why we needed to understand a more fundamental question first. What does it even mean for a hardening compiler to be correct? And as we will see shortly in this talk, this is by far not obvious. To answer this question, we develop a formal correctness criteria and specify hardening compilers using a separation logic. Then we develop a new proof technique to prove the soundness of the logic end-to-end for the compiled program. We also demonstrate our method by verifying a simple hardening compiler from a source language rec, which is a simple C-like toy language with undefined behavior, to a target language cap, which is an idealized assembly language with capabilities. And all our work is formalized in ROC. So when approaching a new research question, a good first step is to study the literature. And in fact, there's a related problem studied in literature called robust safety preservation. Preservation in the sense that it's a property about a compiler that compiles programs written in a secure source language that are robustly safe, such that all programs that are robustly safe in the source language also need to be robustly safe after compilation. So robust safety needs to be preserved. In other words, a malicious low-level context should not have any extra power to break safety. You can see that this looks quite similar to our problem, since the goal is the same. However, in our setting, there's nothing to be preserved, since the source language, our source language, is not secure, and hence the source program cannot be robustly safe. So the goal, robust safety of the compiled program, is clear, but a question for even specifying a hardening compiler is what programs can a hardening compiler make robustly safe? I mean, clearly our motivating example from the beginning should be made robustly safe by the compiler, but not all programs can be made robustly safe. If a program, for example, deliberately shares its private variables, then there's nothing meaningful a compiler can do about this. Once a pointer is shared, we lose its integrity. So what program should a hardening compiler make robustly safe? Well, I mean, intuitively that's somewhat clear. All programs that would be robustly safe if C would be a safe language. But the question is, how can we formalize this intuition? Our idea is to use a program logic to characterize all programs that should be robustly safe, should be made robustly safe by a hardening compiler. Concretely, we propose a logic reckon, which is a separation logic built on Iris and inspired by OCPL. Reckon tracks what pointers have been shared with untrusted code. So a pointer can either be exclusively owned by a program or shared with untrusted code. For the first part, we use the standard separation logic points to that expresses ownership of a location, or exclusive ownership of a location, together with the information that this location currently stores some value B. Reckon then additionally comes with a low integrity points to that expresses that some location has been shared with untrusted code and that a value stored at this location is unknown because untrusted code can have changed it. When you have such an exclusive points to on the left, you can trade it in for a shared points to, but there's no way of transitioning back because as soon as you pass a pointer to untrusted code can remember this pointer by storing it in their local state. And then Reckon comes with one central rule, which is this rule here, that allows you to call arbitrary unsafe functions. This rule says that you can execute arbitrary untrusted code as long as all arguments that you pass, all pointers that you pass are low. But let's take a look at an example of Reckon in action. On the left, we have our example from before, and on the right, we have the 3 key ingredients of Reckon that I just showed you. In the beginning, we start with a trivial precondition and then allocate x. This gives us the exclusive knowledge that x stores the value 0. Similarly, allocating private gives us the exclusive knowledge that private currently stores 42. Next in the program, we have this call to an untrusted function. For that, we would like to use the rule that Reckon provides, but in order to use the rule, we need a low points to for the argument. So we use this one-way transition, trade in our exclusive points to for x, and get a low integrity points to. With that, we can use the rule and then frame around the private points to for, or the exclusive points to for the private variable around this function call, such that afterwards we still know that private stores 42 and this assert succeeds. So this is Reckon, and with that we can answer the question of what programs a hardening compiler should make robustly safe. All programs that are intuitively robustly safe, which we formalize using a program logic. So the answer is all programs that can be verified in Reckon. And with that, we found an answer to the first question that I listed as our contribution. We found a formal correctness criteria for hardening compilers. The big open question is, how can we verify it? And effectively, this reduces to the soundness of the logic. But the key rule of the logic is not sound if the untrusted function is implemented in the C-like source language. I mean, that's the reason why we needed a hardening compiler in the first place. So the soundness statement that we prove is this end-to-end result, that our logic Reckon is sound if you compile the program with this hardening compiler, and then the compiled program is robustly safe. We factor the soundness proof into 2 steps. The first step is to prove the soundness of all the normal rules like load and store and similar. There we follow the standard approach of proving the soundness of these rules against the source language and then proving compiler correctness so that a compiled program refines the source program and therefore also fulfills these rules. So this first step is non-trivial, but does not require any fundamentally new technology. However, the second step is to show that arbitrary untrusted functions follow this rule and can be safely executed if all argument pointers are low. Note that this rule more importantly says that low points tos for all arguments are enough to execute untrusted code safely, and that all other exclusive points tos can be framed around and are preserved by untrusted code. Now the problem here is that we need to prove this rule for all low-level contexts, but the rule is stated in a program logic for the source language, so we have different languages there. Again, we want to take inspiration from the literature. The standard approach to reason about programs that interact with untrusted low-level code is a technique called backtranslation. The idea is to, given a low-level context, construct a source context that does the same attack. If the source language is now secure, then the source program is robustly safe against this constructed context. And with that, because this low-level context performs the same attack, one also knows that the compiled program is robustly safe against this low-level context. However, constructing the syntactic back translation explicitly is painful and unfortunately not even enough in our setting, where the source language is unsafe. One would additionally need to prove that all constructed programs fulfill the rule of the program logic, which is not obvious since arbitrary source contexts do not fulfill this rule. That's why we develop a new semantic proof technique. The idea is to leave the syntax behind, since on the semantic level, we can easily characterize all programs that fulfill the rule. We do this by defining a semantic source context that we call sim, and then show that sim over-approximates all low-level contexts by a new proof technique that we call semantic back translation. For convenience, we already moved to the semantic domain at the target level and define a universal contract that semantically over-approximates all possible low-level contexts. Then, semantic back translation does not need to worry about syntax at all, and we only need to show that sim simulates UNIF. The key part of this approach is how we define this UNIF and sim. And I want to use the rest of this talk to give you an idea of how we define them. We define them using DIMSUM. DIMSUM is a multi-language semantics framework developed by Samler et al. It was originally developed for compositional compiler correctness. In DIMSUM, programs are given as semantics as label transition systems with call and return events for the source language and jump events for the target language. For example, our running example from the beginning becomes this transition system here that has call events with the current call and return events with the current global heap attached to the event, and all other operation becomes silent tau events. In this setting, we can now define UNIF and SIM as non-deterministic transition systems that non-deterministically perform all possible attacks at the same time. And the cool thing is that we can define SIM such that it by definition has the key property we want it to have. We can define SIM such that it directly fulfills the rule of the program logic. For this, we use a very handy feature of DIMSUM. Namely, DIMSUM allows to define non-deterministic transition systems with separation logic side conditions. We use this feature for a new purpose to define a transition system that implements an axiom of a program logic by definition. So the trick is to define SIM to listen to all call events and then emit return events and put a pre and post condition as a separation logic side condition. Concretely, SIM listens to all incoming calls such that the precondition of the HOR rule, together with a separation logic frame, holds at a current state interpretation for the current heap. For the outgoing event, we put a post condition of the HOR triple as a side condition. Then SIM non-deterministically performs any attack such that any attack to the heap, such that the post condition is satisfied on this heap. Technically, we require that the state interpretation needs to be updated to this new heap while preserving the separation logic frame. You can see that this way we can define SIM just to be strong enough for the soundness of the program logic, which minimizes our back translation effort. And on my final slide, I want to give you an idea on how this semantic back translation proof looks. Ultimately, we want to show that arbitrary untrusted low-level code is simulated by SIM. One instance of this untrusted code could, for example, be this transition system. We first over-approximate this by a non-deterministic transition system that does all attacks at the same time. So maybe the second branch of this transition system could be the concrete instance of the untrusted code we have on the left. We saw how we define SIM as a transition system with separation logic side conditions. Here, we additionally wrap it in a so-called wrapper that we inherit from DIMSUM. The wrapper translates between source and target events such that we can then relate sim to the untrusted low-level code. And then we need to prove that UNIF refines sim. Here, the trick is to define UNIF in the same shape as sim. So also as a non-deterministic transition system with separation logic side conditions. For that, we define a low predicate for target values and assert that all values in the registers are low. Then, semantic backtranslation, in a sense, boils down to translating between the low predicate of the source and target language, and is surprisingly easy after all. The paper goes into a little more detail, but this is the basic idea. And with that, I want to summarize. We prove robust safety for an unsafe language that is established by a hardening compiler. As a characterization criteria, we propose to use a program logic with this simple rule that characterizes the guarantee that the compiler gives independently of the concrete implementation. As a proof technique, we propose a novel technique that we call semantic backtranslation to prove the soundness of the program logic end-to-end for the compiled code. Thank you.
We have a few minutes for questions.
Hello, thanks for the talk. There was a slide where you said Recon does not have step indexing. Could you say a bit more about that, and what is the reason?
Yes, that's basically a limitation we inherit from dim sum. Yeah, we don't have step indexing because yeah, basically the technical reason is you saw. On this slide, we have the satisfiable predicate, and there we basically assert that the separation logic proposition is satisfiable at the step index 0, and therefore we don't have step indexing in this logic.
Okay, so thanks for this talk. I was wondering, can you go maybe to the next slide so it's clear to everybody?
Yes.
So yeah, this UNIF in blue
yes.
Over approximate arbitrary target context.
That's
and you
true.
create a single red sim, right, for
Yes.
this UNIF. So, I mean, if you have some familiarity with that work you were talking about the preservation of robust safety, this means you are creating, there is one single source context that kind of works for arbitrary target context. So I suspect that you have much stronger properties than robust safety. But we can take this offline and maybe if you didn't look into it.
Yes, so in this work we only target robust safety.
Yeah.
But yeah, it's future work to find out what exactly we get there.
Okay.
Yeah,
Thanks.
it depends a little bit on how you exactly define UNIF and sim.
Thank you.
Hi, thanks for the talk. This is really interesting. I think you mentioned that there are some programs which can't be made robustly safe.
Yes.
The example you gave was sort of degenerate. Are there like useful programs that can't be made robustly safe?
Useful programs that can't be robustly safe. I haven't really thought about this. I mean, as soon as a program shares pointers with untrusted code, it basically gave up all invariants it has on these particular pointers. So yeah, I don't know. So in order to be robustly safe, programs need to be aware of that and, well, like, don't share pointers where they have invariants on with untrusted code.
Hello. Hello. Oh, so when you're compiling the low-level code, I mean, you do have to have a C compiler that is compiling the untrusted code, and then you have to actually have some kind of capability protections or something like this that actually implements that behavior of hardening that you describe. I mean, basically this presentation seemed to be about the separation logic side of things, but at some point you actually have to implement this behavior in the compiler. Like what is the compiler doing?
Okay, yeah, first of all I need to clarify, we don't compile the untrusted code. We only compile the program we reason about, and then the program can be linked with any arbitrary untrusted low-level code that can either be compiled or it can be a maliciously crafted low-level binary. Yes, but what does the compiler do? I mean, clearly we built a simple toy compiler in this project that basically does what I said in the beginning. It compiles local variables to capabilities with disjoint bounds, and then makes sure if a program passes a pointer to untrusted code, then the compiled program only passes like a capability with bounds only to this local variable.
So are you relying on hardware protections in order to do
stop
this?
here and take the rest of the conversation offline so that we can move to the business meeting.
Thank you.
Thank you very much.